Let's see how quickly we can go through everything you need to know for Edexcel A-level Physics. And don't forget to check out our revision app to help you test your knowledge. Links in description. All particles are put into the groups hadrons and leptons. Leptons are fundamental particles and they include the electron, muon, that's just a heavy electron essentially, and neutrino, that has no charge and essentially no mass. These all have a lepton number of 1, whereas their antiparticle equivalents have a lepton number of -1. Neutrinos can also be specifically electron neutrinos or muon neutrinos, so you have to treat their lepton numbers separately if an interaction involves both electrons and muons. Hadrons are split into baryons made of 3 quarks and mesons made of 2 quarks, a quark-antiquark pair. So hadrons aren't fundamental particles. The 3 flavors of quark we deal with are up, down, and strange. Up has a charge of +2/3 e, down and strange -1/3. Only strange quarks have strangeness. -1 for a strange quark, +1 for an anti-strange. After all, they are strange. These quarks have a baryon number of +1/3 each, so baryons have a baryon number that isn't 0. It can be +1 or -1 if you have antiquarks in there too. Neutrons are up, down, down. Protons are up, up, down. So you can say the nud and the pood to help you remember them. Anti-up, anti-down, and anti-strange quarks have the opposite charge and baryon number. Pions are mesons that don't have strangeness, whereas kaons are mesons that do have strangeness. We can call them pi plus, pi 0, pi minus, and k plus, k minus, k 0, etc. to distinguish between them. The electromagnetic force can affect any charged particle. The exchange particle is the photon. We might say virtual photon. It's just a certain way of explaining forces between particles in terms of momentum transferred. Gravity's exchange particle is called the graviton, but you know about those 2 forces already. Let's go with the 2 that are new to A-level. The weak force or weak nuclear force can affect pretty much any particle. Its exchange particle is the W+, W- or Z0 boson. The strong nuclear force only affects hadrons on the other hand. Its exchange particle is the pion or gluon, if pion isn't an option in a question. This force is what holds nuclei together. The electrostatic repulsion between protons pushes outwards, while the strong force pulls inwards. Okay, a bit of gravity too, but that's really not that much. When these forces are balanced, a nucleus is stable. The range of the strong force is 3 to 4 femtometers, but it switches from attractive to repulsive at 0.5 femtometers to stop the nucleus from imploding on itself. In any interaction, charge, baryon number, and lepton numbers must be conserved, which is why there must be an anti-electron neutrino added in a beta- decay equation to balance the lepton number. We can draw Feynman diagrams to represent these interactions. This will pretty much always be a weak interaction involving a W- boson, say for a beta- decay, or W+ boson for beta+ decay, or electron capture. For normal beta or beta- decay, we can also just say that one of the down quarks in the neutron is decaying to an up quark, and that turns the whole thing into a proton. It goes from nud to pood. The term radiation means any particle or wave that's emitted by something. The electromagnetic spectrum is all radiation, but they're all emitted by electrons. Well, all apart from gamma. Gamma radiation is actually emitted by the nucleus of an atom. If it has excess energy, it's getting rid of. Gamma rays are high-energy EM waves. They can be dangerous as they can ionize atoms if absorbed by them, knocking electrons off. This can cause damage to the cells in your body and cause cancer. But there are 2 other types of radiation nuclei can emit too, but these are actual particles and they're emitted when nuclei decay. Change. Isotopes with more neutrons are generally more unstable and more likely to decay. Heavier nuclei like americium-241 decay by what we call alpha decay. To become more stable, the nucleus will emit a bundle of 2 protons and 2 neutrons, what we can just call an alpha particle. This is alpha radiation. This is what the nuclear decay equation would look like for this to show that the nucleus has decayed into 2 parts. The alpha particle, which must have an atomic number of 2 and a mass of 4. And the daughter nucleus, that's just the nucleus left over, which of course is no longer going to be americium as it's lost protons to go from an atomic number of 95 to 93. Turns out that's now neptunium. You'll never have to remember these elements, you just need to worry about the numbers. It's just maths. 95 goes to 93 plus 2, and the mass is similar. 241 goes to 237 plus 4. There is actually a nucleus that has the numbers 2 and 4. It's a helium nucleus. That's what an alpha particle is. Lighter isotopes, lighter nuclei, like carbon-14 decay by beta or beta- decay instead. What happens is that a neutron in the nucleus turns into a proton and an electron. But the fast-moving electron that's ejected by the nucleus escapes, and we now call this beta radiation. The mass of an electron is basically 0, so we put that on top for that. It has the opposite charge to a proton though, so we say it has an atomic number of -1. Now be careful here, 6 goes to what? Plus -1? No, it's not 5. It's 7. 6 is equal to 7 plus -1. So like we said, a neutron has turned into a proton. So the nucleus has gained a proton. It's gone from 6 to 7. The mass, however, is unchanged. So it's still 14. And don't forget to add the anti-electron neutrino on the end to balance the lepton number. If a particle and its corresponding antiparticle meet, say an electron and positron, they can annihilate, and all of their mass is converted into energy in the form of 2 photons of EM radiation. It's 2 photons, by the way, as momentum must be conserved. And even though photons don't have mass, they still have momentum, weirdly enough. If we're asked to find the minimum energy or frequency the photons made, we infer that they had no kinetic energy. So we just say that energy equals 2 lots of mc squared. We call this either rest energy or mass energy, where c is the speed of light. We can then say this is equal to 2 lots of hf, which is the energy of a photon, Planck's constant times the frequency. The shortcut, of course, is just to split the whole problem in half. We can just say that mc squared for one of the particles equals hf for one of the photons. The opposite can happen when a photon spontaneously converts into 2 particles, if it has enough energy. This is called pair production. This time, hf is equal to 2 lots of mc squared because it's just one photon making 2 particles. If the photon has more energy than the minimum energy needed, the extra energy is supplied to the particles as kinetic energy. It's the opposite for annihilation. If they have kinetic energy before, that also goes into the energy of the photons afterwards. Electricity is the flow of charge, or charges like electrons. They carry energy from a source of energy to a component. By the way, you're going to see me mix up cells and batteries in this video because they're just the same thing, really, and they do the same job. The battery has a store of chemical potential energy. When connected in a complete circuit, this energy is transferred to the electrons, which move through the wires. This movement of charge is called a current. And we say it always goes from the positive terminal of a battery to the negative. You might realize that that seems a little bit backwards, but that's just the way it has to be. It's convention. As the electrons pass through the bulb, their energy is converted into light. But the electrons don't just disappear once they transfer all the energy to the bulb. As this is one big loop, these electrons are pushed back round to the battery by the ones behind them, where they're refilled with energy, ready for another trip round the circuit. This constant flow of electrons transferring energy is what keeps the light bulb on. We don't deal with individual electrons, but instead deal in coulombs of electrons, or coulombs of charge. Potential difference, PD for short, also known as voltage, tells us how much energy is transferred per coulomb of electrons. So if a cell or battery says it's 1 volt, that means that it's 1 joule of energy given to every coulomb of electrons that pass through it. If a battery is 6 volts, that means 6 joules is supplied per coulomb instead. We measure PD with a voltmeter. They're always connected in parallel across the component you want to measure the voltage of, the PD of. In the real world, that means the leads or cables from the voltmeter always piggyback onto other leads. If we put the voltmeter across the battery, it should measure 6 volts, right? Because 6 volts is supplied to the electrons in the circuits, 6 joules per coulomb. But put it across the bulb, and it still says 6 volts. Why? Because the electrons have to lose all of that 6 volts worth of energy as they pass through. Here's the equation for PD. PD in volts is equal to energy in joules divided by charge in coulombs. In symbol form, V equals E over Q. Q is the symbol for charge, but it's measured in C in coulombs. Current, on the other hand, tells us what the rate of flow of charge is. Like any equation for a rate, as per usual, it's something divided by time. So here it's current in amps equals charge in coulombs divided by time in seconds, or I equals Q over T. We measure current with an ammeter. Note that it's not amp meter. Unlike a voltmeter, it must go in series. This means in line. Components in a circuit have resistance, that is, they resist the flow of charge or current through them, but that's not a bad thing. This has to happen in order for them to work. A bulb has resistance, which causes energy to be transferred and light to be emitted. A resistor, of course, has resistance too, but it just produces heat when current flows through it. If you make a circuit with a resistor and change the PD available to it, what we find is that an increasing PD results in a greater current flowing. In fact, doubling one doubles the other, so we can say that PD and current, or V and I, are directly proportional. Drawing a graph of these two makes a straight line through the origin, and if we turn the battery round, we can get negative values for both too, but still a straight line. This straight line with a constant gradient shows that the resistor has constant resistance. We say it's ohmic. The steeper the gradient of this line, the lower the resistance of the resistor, as more current is flowing per volt. The equation for resistance is Ohm's law, V equals IR. We can get the resistance of a component from an IV graph like this by picking a point on the line and rearranging Ohm's law, so R is equal to V over I. For a resistor, you'll end up with the same answer no matter what point you pick. If you repeat the same experiment for a bulb in place of the resistor though, you'll end up with a curved graph like this instead. This shows that the resistance is changing, the resistance of the metal filament in the bulb. In fact, you'll find that any metal has a changing resistance if you increase the PD and current. They're non-ohmic. At higher PDs, the current increases less and less, so that means they can't be proportional. This shows that the resistance of the metal is increasing with higher PDs and higher currents. The changing gradient shows that this is true, but we still just take a point on the line and use Ohm's law if we want to find the resistance. It's just that it does matter where you pick the point in this case. Note that we never draw a tangent on a curved IV graph. The gradient doesn't give you anything. So why does resistance change for a metal? Well, it's because metals consist of a lattice or grid of ions surrounded by a sea of delocalized electrons. That just means that they're free to move, or rather, fairly free to move, as they do collide with the ions as they flow. That's why the metal heats up when you pass a current through it. The higher the current, the more frequent these collisions are, and this makes the ions vibrate more and more, which in turn makes it harder for the electrons to flow. The resistance has increased. Now, there is another component called a diode. It will give you this graph. The circuit symbol might give you a clue as to why this is. A diode only lets current flow in one direction. We say that in one direction the resistance is very high and it's very low in the other, which is why the current suddenly increases at around 1 volt. An LED is a light-emitting diode, similar symbol, just with a couple of extra bits showing that light is emitted. These are what most lights in electronics are these days, rather than filament lamps. A superconductor is a material that can have a resistance of 0. Not nearly 0, actually 0. Generally, these materials need to be cooled before they reach this point though, so you might see a graph like this. As the temperature goes down, so does the resistance, until boom, we hit what we call the critical temperature. Below this critical temperature, the resistance is 0. Every material has a different resistivity, or resistivity some people say. The definition is this: it's the resistance of a cube of unit length sides of that material. So in SI units, that's the resistance in ohms of a 1 meter cube. Note that this is not resistance per meter cubed. The definition must involve an actual cube. The unit we use is therefore ohm meters. Again, be careful, that's not ohms per meter. To find resistivity, we measure the diameter of a wire with a micrometer and calculate area from that using pi d squared over 4. We then measure V and I to calculate R for varying lengths of the wire measured with a meter rule. Plotting R against L gives a proportional relationship. The equation for resistivity, therefore, is this: R equals rho L over A, where rho is resistivity in ohm meters. Rearranging this, we have rho equals RA over L. The gradient of the graph is R over L, so multiplying by this area gives us the resistivity. Here's the simplest series circuit we can make, just two resistors in line with the battery. What you need to remember is that for components in series, total PD is shared between them, current is the same for all of them, and the total resistance is just the sum of all the resistances. They're just added up. Let's deal with that first point. If these resistors are the same, let's say 10 ohms each, then that 6 volts total PD from the battery must be shared between them. So if we put a voltmeter across each of these, they both read 3 volts. It wouldn't matter what resistance these resistors are, they could be 1,000,000 ohms each. If they're the same, then that total PD is shared equally. By the time the electrons leave the second resistor, they have to have lost all 6 volts worth of energy, ready to go back to the battery to be refueled. This idea is actually just Kirchhoff's second law. The sum of EMFs must equal the sum of PD drops in a closed loop. Just remember that if batteries are pointing in opposite directions, one of them must be a minus EMF. By the way, we can also call this setup a potential divider circuit, as the total potential, total PD, is being shared. If the resistors don't have the same resistance, then we can use the second point to help us. That is, the current is the same for both. Let's say that the first resistor is 20 ohms using 4 volts of the total 6 volts available. We know two things out of V, I, and R. So let's use Ohm's law to find out what the third unknown thing is, current in this case. Rearranging Ohm's law, we get I is equal to V over R. So that's 4 divided by 20, 0.2 amps. Same for the second resistor too. But is there also a second thing we know about the other resistor? Why, yes, there is. Remembering the first rule up here, we know that if the first resistor is using 4 volts of the total 6 volts available, while the other resistor must be using 2 volts. We could then use Ohm's law again to find its resistance, 10 ohms. The rule of thumb is this: the greater the resistance, the greater the share of the total PD it gets. We can also use Ohm's law for a whole circuit. We just need to make sure we're dealing with the total PD, total current, and total resistance. The rules for parallel circuits are the opposite. The PD is the same for every branch, Again, this is true because of Kirchhoff's second law. The battery is actually involved in two loops, you see. So therefore, the PD drops in both loops must be the same. Current is shared between each branch, and the more resistors you add in parallel, the lower the total resistance. This, by the way, is because you're giving the current more routes to move through the circuit, which means more current can flow. So if these two resistors are connected to the 6-volt battery in parallel, you know straight away that the PD for both has to be 6 volts. Voltage is not shared in parallel circuits. If, however, we say 0.5 amps total current is flowing through the battery and 0.2 amps of that is flowing through the top resistor, that means there must be 0.3 amps flowing through the bottom resistor. This is actually Kirchhoff's first law. Total current into a junction equals total current out. If you're not in a rush, why not pause the video and see if you can calculate these two resistances. By the way, if you want a little bit more help on this, then have a look at my video, How to Answer Any Electricity Question. It's not only metals that can change resistance, we can have a thermistor and you can have a circuit that responds to changes in temperature. A thermistor's resistance decreases if the temperature increases, so in essence it does the opposite to a metal. By the way, you might see it called an NTC thermistor, negative temperature coefficient. That just means the higher the temperature, the lower the resistance. In this case, if the resistance increased, the resistance of the thermistor would go down, as does its share of the total PD. That means the PD measured by this voltmeter here will increase. This could be the basis of a temperature sensor for your central heating, for example. An LDR is a light-dependent resistor, very similar to a thermistor, but resistance goes down with increased light intensity, not temperature. So this circuit could be on the top of a street lamp, for example. Light intensity goes down, resistance of the LDR goes up, as does its share of the voltage. This could then be connected in some way to the light bulb, so it turns on as it gets dark. Power is the rate of energy transferred, so energy divided by time. However, when it comes to electricity, P equals VI. A battery or cell produces DC, direct current. The PD and therefore current only ever point in one direction. Electronics need DC to work generally. However, AC, alternating current, is needed to transmit electricity over long distances, say through the national grid. This is because transformers are needed to step up the voltage, reducing the current before it enters the grid. The neutral wire in mains stays at a potential of 0 volts, while the live wire varies between plus 325 volts and minus 325 volts. So we say the peak voltage is 325 volts, and we might say the peak-to-peak voltage is 650. However, to do any measurements with AC, we must convert it to a DC equivalent by using root mean square values. To convert from peak voltage to RMS voltage, or VRMS, the conversion factor is root 2. 325 divided by root 2 gives us 230 volts, which you probably know is what UK mains voltage is known to be. It's the RMS value we're given. And it also works for current too. To go from peak power to mean or average power, it's a little bit different. We don't call it RMS power, by the way. It's not quite the same. It turns out batteries and cells have a resistance of their own, so if you attach a bulb to a 6-volt battery, the bulb will get less than that. A voltmeter across it might measure 5.5 volts, say. This would also be the same if we attached the voltmeter across the battery terminals instead. So we can call this the terminal PD. Be careful, this means the voltage available to the circuit. That means 0.5 volts is being lost inside the battery due to its internal resistance, little r. The EMF, electromotive force, epsilon is the symbol we use, is the total PD provided. That's the 6 volts here. So the equation is this. EMF equals terminal PD, V, plus I, little r. So I times little r is the voltage lost due to the internal resistance. If we increase the load resistance, that's the resistance of the circuit, the current flowing through the battery decreases, of course. But this results in less PD being lost in the battery. So the terminal PD increases. Drawing a graph of terminal PD against current gives us a straight line. The magnitude of this gradient is equal to the internal resistance. If we extrapolate the line back to the y-axis, the y-intercept is equal to the EMF, which makes sense, as if there's no current flowing, then in theory the circuit should get the whole of the EMF. There's no volts lost in the battery. You can, of course, get the EMF by just attaching a voltmeter across the battery by itself with nothing else connected. This works as voltmeters generally have very, very high resistance, so essentially no current is flowing. We can represent forces with vectors, that is an arrow that shows the direction and magnitude of the force. If two forces act on an object, there's a resultant force. We find this by technically adding the vectors. However, if they go in opposite directions, one must be negative. So in this case, the resultant force would be 3 newtons to the right, and that's positive if we've decided that positive is in the right direction. If vectors are at right angles to each other, we use Pythagoras to find the resultant. This works because you can make a triangle by moving one of the forces, so they're top and tailed. You could also be expected to use trig, that's SOHCAHTOA, to find either one of these angles. If a measurement or quantity just has magnitude but no direction, it's not a vector, but it's called a scalar instead. Here are some examples of both. Note that displacement is distance traveled with a direction. Similarly, velocity is the vector form of speed. Weight is another name for the force due to gravity that acts on an object. It's calculated by multiplying the mass in kilograms by gravitational field strength, or G, which here on Earth is 9.8 newtons per kilogram. Now, if you hold an object up with your hand, you must be pushing up with a force that is equal to its weight in order for the forces to be balanced and so it doesn't accelerate. However, that means that if you lift it upwards at a constant speed, that's also true. We can therefore then calculate the energy that is used to lift this object by using the equation for work done. Work done is just another way of saying energy transferred by a force. And it's equal to force times distance moved. The equation is true for any situation, but in this case, the force is the weight and the distance is the height. So we could say the work done is equal to the gain in energy, and that's equal to m times g times h. Does that look familiar? Well, it should, because that's the exact same equation for calculating GPE. That's GPE gained, to be precise. To use the work done equation, the force and distance moved must be parallel. If the force is at an angle, however, we must resolve it to find the component that is parallel to the distance. That's why sometimes you'll see a cos theta on the end of the work done equation in your formula sheet. If we divide both sides of the equation by time, we end up with power equals force times velocity. We sometimes call this power developed. It just tells you how much work is done per second by or against a force. Newton's first law is this: when there's no resultant force, an object's motion is constant. In other words, no change in velocity. That could be because there's no forces acting on the object, or the forces are balanced. Newton's second law involves unbalanced forces, that is, there is a resultant force. This is equal to ma, mass times acceleration. Only one of these laws can be true in any situation. There's either no resultant force, or there is one. Newton's third law, however, is always true, and this is the one that people get confused about, understandably. For every action, or force, there's an equal and opposite reaction, force. But this is not referring to balanced forces. It's all about perspective. When we think about the first two laws, we only really consider the object itself. For example, the force pulling downwards on the ball is its weight. We know that the Earth is pulling down the ball, but Newton's third law says the complete opposite is true as well. The ball is also pulling the Earth up. Now, the Earth is so massive that it doesn't really have an effect on it, but it's still true nevertheless. Another example, if you have two ice skaters, if the guy skater pushes on the girl skater, there's an equal and opposite reaction force pushing back on him too. That's why they both move away from where they were. If an object is on a slope, its weight, mg, will try to pull it downwards. However, the reaction force of the slope pushes perpendicular to the slope. This is equal to mg cos theta, where theta is the angle of the ramp. For an explanation of where the angles come from, check out my mass on a slope video. The combination of these two forces add up to a resultant force that pulls down parallel to the slope. This is equal to mg sine theta. That's always going to be true, no matter what the object is doing. If it's stationary or traveling at a constant speed, that must mean another force is pushing or pulling up the slope. That has to be equal to this component, mg sine theta. Quite often that's friction. No matter what forces are involved though, you'll find the resultant like you do for any other situation. The sum of all forces in one direction minus the sum of all forces in the opposite direction. Then you can use this resultant force in F equals ma. If you're given the height of the ramp, chances are you're going to have to use energy too. Maybe the mass is sliding down the ramp, for example. If there's no frictional forces, we can say mgh at the top equals half mv squared at the bottom. But if you're told the speed at the bottom, chances are some energy is being lost instead. So in that case, we use the work done equation, with the work done being the energy lost. And that can give us the average frictional force. Just remember that the distance has to be the distance traveled, not the height in that case. If an object is accelerating, we use one of Newton's equations of motion and their Suvat variables. If an object is only moving in one direction, S, U, and V can all be positive, even if it's downwards. You do have to be careful with A, acceleration though, as that could be negative, for example, if the object is decelerating. In any question, you write down your variables and the unknown you need to find. Cross out the unused fifth variable, choose the right equation, and rearrange if necessary. To deal with an object being thrown upwards and returning to its original position, S is technically 0 and things can get a little bit messy. In this situation, it's always a good idea to split the problem in half from start to the apex, where V ends up being 0, and then just double the time if the question requires it. For objects being fired horizontally off the edge of something, say a cliff, you split the problem into vertical and horizontal. Use suvat for vertical motion, where u is 0, as the initial speed it's traveling with is only horizontal. A is equal to g, that's 9.81, and s is the height it falls. Chances are you're going to use s equals ut plus half at squared. Ut disappears because u is 0. Don't use suvat for the horizontal motion, as the horizontal velocity stays at that initial speed, so horizontally you just use speed equals distance over time. For objects fired at an angle, you need to resolve the initial speed into horizontal and vertical velocities. Check out my easy vectors trick video for the best way on how to do that. Again, we use suvat for vertical, speed equals distance over time for horizontal, and again we use suvat for vertical and speed equals distance over time for horizontal. Like the ball being thrown upwards and coming back down, you might need to split the trajectory in half and just go from the start to the apex. Momentum is equal to mass times velocity. The unit, therefore, is kilogram meters per second. Momentum is a vector, which means you have negative momentum if your velocity is negative. In a collision, kinetic energy isn't always conserved, but total momentum always is. Calculations on this can be tricky, but you just have to be careful with your pluses and minuses. You write down m1 u1 if there's just one object moving to begin with. Remember u from suvat, we can use it here too. And add on m2 u2 if there's a second object moving to begin with too. This then is the total momentum before the collision, before the event. This could also be 0 if nothing's moving to begin with, say a cannon about to fire. Then all we have to say is that this is equal to the total momentum afterwards, m1v1 for one object, plus m2v2 if there's a second object moving too. If they've coupled together, we just say m times v, where m is the total mass of the two. Then all you have to do is pop your numbers in, making sure that everything traveling to the left, say, has a negative velocity, and you'll be left with one unknown. Rearrange to find it. Incidentally, in the case of the cannon, as there's 0 total momentum before, the same must be true after as well. Even though the cannonball is moving, that must mean the cannon has the same momentum as the cannonball, but in the opposite direction, so they still add up to 0. This is an example of recoil. One last and very important example is rebound. When an object or particle collides with an object that essentially doesn't move, say a wall, it will rebound with the same speed, but in the opposite direction. That's not a 0 change in momentum though, as momentum is a vector. If its initial momentum is mu, where u is the initial velocity, then the change in momentum, also known as impulse, will be minus 2 mu. Of course, total energy is always conserved too, that's just fundamentally true, but some of that will likely be lost to the surroundings as heat and sound, etc. Total kinetic energy is very rarely conserved as a result. We call such collisions inelastic, like two plasticine balls smushing into each other. There's no kinetic energy afterwards, so that's as inelastic as you can get. If the conditions and the objects are just right though, you can get collisions where the total kinetic energy is conserved in theory. These are elastic collisions. An example of this would be snooker balls hitting each other, or a Newton's cradle. Force and momentum are closely linked. Newton's second law says that F equals ma, but we also know that A is equal to delta V over t. But actually it's also true that force is equal to change in momentum over time, or we can say the rate of change of momentum. That's why the alternative unit for momentum is Newton's seconds. If you draw a graph to show how the force acting on an object changes over time, the area under the graph gives us the impulse, the change in momentum. So if the object was stationary initially, it will now have that momentum due to the impulse provided to it. If a fluid, like air or water, pushes on something at a constant rate, say a hose pipe spraying a wall, or air through a wind turbine, we can find the momentum carried per second by it. In essence, this is the same thing as force, as you know from our equation. Units are your friends here, as you won't be given an equation for this. So let's take F equals delta mv over t, but instead of swapping v over t for acceleration, we split it into m over t times v. M over t is the mass in kilograms moving per second, but you'll more likely be given the density of the fluid instead and the cross-sectional area that it's moving through. So mass is equal to density times volume, and volume is equal to area times length. Length over time gives you speed, so the most useful equation for this is F equals rho av squared. A moment, or torque, is a turning force around a pivot. It's calculated by force times distance to the pivot, so its unit is Newton meters. However, it's not the same as work done, as force and distance must be perpendicular in this case instead of parallel. If they're not perpendicular, you must resolve one of them, usually the force, by multiplying by sine or cos theta, depending on what angle you're given. Again, have a look at my easy vectors trick video. In short though, we multiply by cos theta if the angle is between the resultant and the component, and sine theta if not. The principle of moments is this. For an object to be in equilibrium, the sum of clockwise moments must equal the sum of anti-clockwise moments. Bear in mind an object can already be spinning and this still be the case. In reality, there is another condition needed for an object to be in equilibrium, which you already know. There also can be no resultant force acting on the object. It turns out that the principle of moments can be applied to any scenario, even if there appears to be no pivot as such. In fact, you can make any point your imaginary pivot and it still works. For example, this guy standing on a plank resting on two supports. You first take moments about one of the supports to eliminate it from the equation. If we take moments about the left support here, the moments due to the weight of the plank, which is easily forgotten about, and the dude going clockwise must be balanced by the moment due to the reaction force from the support on the right. You can find the reaction force this way, and then you can use this with just balanced forces to calculate the reaction force on the left. If you have two unknowns, you must use moments, but if you just have one unknown force left, you can just use balanced forces. A couple is defined as two forces acting in opposite directions on an object such that they produce a resultant moment but no resultant force, meaning that the object will start to spin if it wasn't already, but will not accelerate. It won't start moving if it was stationary before. It's not an equilibrium, as it's only satisfied one of our two conditions. An object will topple over if its center of gravity has moved past the pivot vertically, so the moment due to its weight has changed direction from clockwise to anti-clockwise or vice versa. For something moving in a circle, only one condition needs to be satisfied. There must be a force that continuously acts at 90 degrees to the object's velocity or direction of motion. That means that its velocity and direction of travel constantly changes, but it still travels at a constant speed. As velocity is a vector, it's still accelerating because the direction of the velocity is changing, even though the magnitude of the velocity, the speed, is not. This centripetal acceleration is equal to v squared over r, where r is the radius of the circle. As F equals ma, the centripetal force is equal to mv squared over r. As speed is equal to distance over time, we can calculate it by doing circumference divided by the time period, so 2 pi r over t. It's also useful to consider its angular velocity, also known as angular speed or angular frequency. That's how many radians of the orbit are covered every second. We give it the symbol omega, a curly w. That's equal to 2 pi f, or 2 pi over t. How many radians per second? That means that v equals omega r. This is actually a very important equation that people often forget. Replacing v in our centripetal acceleration and force equations, we end up with the alternative versions, a equals omega squared r and f equals m omega squared r. If you're given the time period, you use the omega versions and replace the omega with 2 pi over t. If you're given the actual speed though, you use the first equation, a equals v squared over r, or f equals mv squared over r. Similar to angular velocity, angular displacement is just how many radians an object has turned through. If it's a vertical loop, like a loop-the-loop on a roller coaster, the centripetal force will be due to the support force of the track, but we also have to take into account the weight. We might call the support force S. At the bottom, mg is pulling down and S is pushing up. The centripetal force is one minus the other, or at least that's true if we're just thinking about the magnitudes of the forces. It's the resultant of the two forces. At the top, both are pulling down though, meaning the centripetal force now equals S plus mg instead. In both cases, we usually then equate this to mv squared over r. When it's at either side, weight isn't contributing to the centripetal force at all. Therefore, S is just equal to mv squared over r. A car on a banked track or a banking plane can be tricky, but just remember that it's different from a normal mass on a slope situation. The main force here is the perpendicular reaction force of the track, or the upthrust of the plane, which is at an angle. These forces need to, of course, supply a vertical component that is equal to the weight mg. Usually we need to find out what the centripetal force is, which is pointing towards the center of the circular track, or the plane's circular path. Drawing a triangle shows that this horizontal force is equal to mg tan theta, if theta is to the vertical, as we have the opposite and adjacent sides of the triangle. This is then equal to mv squared over r, and you can see that the m's cancel too. A current flowing through a wire will produce its own magnetic field. The motor effect is when such a wire is in another magnetic field and it will experience a force. The equation is F-bil, where F is force, I is current in amps, L is length of the wire in the magnetic field, and B is the magnetic flux density, essentially the magnetic field strength. This is measured in Tesla. Rearranging the equation for B also shows us that an alternative unit for flux density is newtons per amp per meter. Note that this equation only works as it is if the current and magnetic field lines are perpendicular to each other. So therefore, if the wire is parallel to the field lines, it will experience no force. To find out the direction of the force, however, on the wire, we use Fleming's left-hand rule. Your thumb is force, first finger is field, middle finger is current. Make a janky gun with them where they're all perpendicular and bam, freeze, FBI. Just twist your wrist to line up your fingers with the current and the field, always north to south pole. And the way your thumb is pointing is the direction of the force on the wire. In this case, upwards. To measure the size of the force in reality, we can put the magnet on a balance. Due to Newton's third law, the magnet will also be pushed down with the same force. Calculate the force from the fake mass measured. Use an ammeter to get the current and a ruler to measure the length of the wire. And what do you know? You can calculate the magnetic flux density between the poles of your magnet. If a free charged particle finds itself travelling perpendicular to a magnetic field, it will experience a force equal to BQV. For an electron or proton, we can say thus F-bev. We still use Fleming's left-hand rule, with the current finger now being used for velocity. However, as it's used for conventional current in circuits, which is technically the flow of positive charge, we must flip our hand if it's a negative charge like an electron. So our middle finger is pointing in the opposite direction to its velocity. If it's a proton or positive ion though, it's all good. Because we're thinking in 3 dimensions, you usually see the circular path drawn on the page. Then the field goes in or out of the page. That's represented by crosses or dots. As a circular motion, we can say that BQV equals mv squared over r, or m omega squared r, depending on whether you're dealing with actual speed or frequency in time period instead. Rearranging the first equation, we see that r is equal to mv over bq. So the radius of the circle is proportional to the mass and speed of the particle, and inversely proportional to the flux density and the particle's charge. With the angular version, we know that v equals omega r, so we see that the frequency of a particle moving in a circle is independent of its radius. A cyclotron is a machine that uses magnetic fields to produce a stream of high-energy particles like protons used for medical therapy purposes. We have a source of these particles sitting in the center of 2 hollow metal Ds, so-called because of their shape. A magnetic field is applied perpendicular to the Ds, which causes the protons to move in circles. But they're not much used if they stay in the center. So a PD is applied to the Ds, causing the protons to be attracted to and accelerated towards the negative D and away from the positive one. That increases their kinetic energy and speed and therefore radius too. Half a cycle later, they must be accelerated across the gap again in the other direction, so the PD must be reversed by the time they do this. In order for that to happen, we know that BQV or BEV equals m omega squared r. And replacing V with omega r and omega with 2 pi f, we find that r disappears and f equals BQ over 2 pi m. That means it doesn't matter how big the radius of the circle of a proton is, all the protons will have the same frequency and time period as they move in ever-increasing circles in the Ds. Eventually they spiral out, and that's how we get our beam. Whatever the frequency of the particle's circles is, that's also what the frequency must be of the alternating PD of the Ds, causing the particles to be accelerated. People will often incorrectly say that the frequency must somehow be twice that of the particle's frequency, as it needs to flip twice every time they do a circle. But flipping twice is exactly what a whole cycle is. Every cycle, the particles cross the gap twice. So that PD must be flipped twice too. We can determine what particles we have in a substance by putting them through a mass spectrometer. As BQV equals mv squared over r, we see that r equals mv over bq. If v, b and q are the same for all particles, then the radius of circular motion is proportional to mass of the particle. So that means particles traveling together initially will separate out according to their masses if they enter a magnetic field. B is the same if they're all in the same magnetic field. Q is the same if they're all singly ionized, that is, they've all lost 1 electron. Getting them all to travel with the same speed is more difficult, but it must be done in order for R and M to be proportional. To do this, we have a velocity selector before the main magnetic field. It's a device with a small hole in the end. We have a different magnetic field to the big one applied. So the particles experience a force in one direction, say upward, and an electric field applied in the other direction, say downward. Only particles for which these two forces are equal and balanced will carry on going straight through the hole. For them, EQ equals BQV. Electric force equals magnetic force. The Q's cancel and we find that V equals E over B. Those travelling too fast will be affected more by B and deflect and don't go through the hole. Too slow, on the other hand, and the opposite is true, and they'll deflect the other way instead. Those going just the right speed for our two fields make it through. Now we have a beam of particles that are all the same charge and travelling in the same direction with the same speed. There are two main designs then. Number one, the particles go through a semicircle in the magnetic field and hit a piece of film. The further along the film the spots are, the bigger the mass that caused them. We can measure this diameter to get the radius and then calculate the mass from that. Brighter spots means there's more of these particles hitting that spot, so it's semi-quantitative. The posher version, though, employs an array of detectors placed at different positions. Which one a particle hits depends on its mass. Of course, these can measure individual particles, so give accurate data on relative abundance of particles in a substance, for example. Flux is what we call the amount of magnetism that an area is exposed to. Symbol is phi, unit is Vebers, but I also like to call them Wubs. Flux density is equal to flux over area. So another alternative unit for flux density, we already have Tesla and newtons per amps per meter, but it's also Vebers per meter squared. It's how concentrated the flux is. Here's a loop of wire in a magnetic field. We can use the area of the loop with the known flux density of the field it's in to calculate the flux filling the loop. Phi equals B times A. Often it's a coil of wire that's capturing the flux, not just one loop. To calculate the total flux affecting the coil, we must take our flux and multiply it by the number of turns in the coil, N. This is then technically called flux linkage instead, but it works exactly the same as flux in calculations. We can also therefore represent flux linkage as BAN, B times A times N. If a loop of wire or a part of a loop experiences a changing magnetic field, an EMF is induced in it. Faraday's law is this: EMF induced is proportional to the rate of change of flux linkage. Now, in reality, the EMF is equal to minus the rate of change of flux, so volts are actually equal to Vebers per second. But because we have that minus, we have to say proportional instead of equal to, but whatever. You have to know that definition. But to all intents and purposes, EMF, voltage, equals rate of change of flux. The classic example is a wire being moved through a field perpendicular to the field. Similar to F-Bill, if the wire was parallel to the field, this wouldn't work. The wire must cut the flux lines, as it were. We know that EMF equals delta phi over delta t, but I'm going to drop the deltas and minus here for convenience. We know that flux is equal to BA. This area is the area of flux swept through, we can say in time t. This area is equal to length of the wire times distance moved. So EMF is equal to BLD over t. Distance over time is speed, so it turns out in this case that EMF equals BLV. Nifty. So why is that minus there? Well, it's to show you that Lenz's law is also true. The direction of EMF induced is such that it will oppose the change that caused it. In other words, an induced EMF or current will try to stop itself being made. It does this by producing its own opposing magnetic field. After all, you know that's what a current flowing in a wire does. The opposing force is the reason why you can't just turn a generator freely. You have to put in work to overcome this Lenz's law. Fleming's right-hand rule tells us the direction of current induced. Same fingers, with the thumb being which way the wire is being pushed. Another example of Lenz's law is a magnet falling through a copper pipe. The pipe experiences a changing magnetic field and an eddy current is induced in it. That just means little circles of current. This produces a magnetic field of its own that opposes the motion of the magnet. That's why the magnet falls slowly through it at a constant speed. If a loop of wire enters a magnetic field, an EMF will be induced as it enters and leaves. While it's inside, the EMF is zero. Now, there are two ways of looking at this. One way is saying that the flux filling up the loop or coil is changing as it enters or leaves. But this stays constant while it's inside, even though it's moving. So therefore, no EMF while it's completely inside the field. The legit explanation, though, is that there is an EMF being induced on both sides of the coil in the same physical direction while it's inside, so they cancel each other out. When entering or leaving, there's only one constant EMF being induced on one side, and so therefore we have an overall resultant EMF. We can calculate this using BLV again. Even if you have stationary coils, you can still induce an EMF in one of them by applying AC to the other. The AC produces a constantly changing magnetic field which the other experiences. This wouldn't work with DC, as that would only make a static magnetic field. In this case, EMF is equal to A times delta B over delta T, because A isn't changing with B, but B is. In this case, you'll likely be given the maximum flux density, and you can just say that's equal to delta B because it will fall to 0 during the cycle, and then we just divide by the time it took to do that. This, of course, is also how transformers work as well. Generators use induction to produce an EMF. As the coil spins, the flux through it goes from a maximum when it's perpendicular to the field lines to 0 when it's parallel to the field lines. The rate of change of flux, however, is greatest when the flux is 0. The maximum flux is BAN, of course, or flux linkage anyway. So if you want the maximum rate of change of flux, we multiply by omega. The peak EMF induced in a generator is equal to BAN omega. The EMF the rest of the time then changes sinusoidally. So the EMF at any point is equal to BAN omega, that's the maximum EMF, times sine omega t or cos omega t, depending on whether it starts at 0 or a maximum, respectively. Don't forget that whenever you use sine or cos for spinny things, they have a pi in, so we have to use our calculator in radian mode. In a power station, instead of a coil spinning between magnets, they have an electromagnet spinning between 3 pairs of coils called stators. These produce 3 separate currents that go off to the national grid. That's why you have more than 2 wires running along pylons. Incidentally, overhead cables aren't made out of copper, as that would be too expensive and they'd be far too heavy. It's light and it's a pretty good conductor, but it's very, very ductile. So to strengthen it, we have a steel core running through the middle. Transformers are used in the national grid to change the voltage at which the electricity is transmitted through the overhead cables. Get this into your head right now though, there is, or should be, no electricity or current in the core. The alternating current in the primary coil produces its own magnetic field, and the iron core acts like a guide for it. We use iron, by the way, as it's easily magnetized and demagnetized. It works well as a guide. This magnetic field induces a voltage and current in the secondary coil. In order for a current to be induced, though, a wire must experience a change in the magnetic field, which again is why we must use AC. The ratio of turns in the coils is equal to the ratio of the voltages. If the secondary coil has double the turns, it has double the voltage and therefore half the current. A step-up transformer increases the voltage before it enters the grid. This then reduces the current, so less energy is lost due to heating. P equals I squared R. The reason I goes down when V goes up is because P is equal to VI, and if it's a perfect transformer, this will be the same across both. The magnetic field reason you have a different voltage induced in the secondary coil is because there are more or fewer turns in the coil to capture the flux that's in the core. In an ideal world, the power in and out of the transformer should be the same. That would mean that it's 100% efficient, so V and I are inversely proportional. However, in reality, they're never 100% efficient, and it's always the current that takes the hit. And so in this case, you stick the efficiency in front of V1I1, for example, 0.8 if it's 80% efficient. We know that Lenz's law explains why it's hard to rotate a coil in a generator. The induced current is fighting back with its own opposing magnetic force due to the motor effect. You can't have one without the other. But Lenz's law also applies to motors too. When a motor spins, the generator effect is also in play. When the motor is turned, an EMF is induced in a coil that opposes the EMF that's driving the motor to begin with. That might sound like a bad thing, but it's actually not. Say there's 6 volts supplied to a motor, but the opposing, what we call back EMF, is 2 volts in the opposite direction, which means that we now have overall 4 volts across the motor instead of 6, and therefore that reduces the power loss due to heating because the current has gone down, P equals I squared R. If a motor is under heavy load, it spins slowly. The back EMF is small and the current is high, so too heavy a load and the motor can burn out. I'm sure you've experienced this when you've smelt the smoke coming from your Scalextric's car when you're holding it down but still pushing the throttle. If a motor is under light load, though, it spins faster, the back EMF is large and the current in the motor is small. Great. We say that objects can experience a non-contact force if they're in a field. Gravitational fields and electric fields work almost identically. It's just that gravitational fields affect all objects and are always attractive, while electric fields only affect objects that have a charge, and they can be repulsive too. You already know that gravitational field strength G has the unit newtons per kilogram. It tells us how much force of gravity is pulling on each kilogram of mass an object has. On Earth, this is 9.81, but the higher you go, the weaker the field gets. This is shown if we draw field lines around the Earth. These show the direction of force, and you can see they diverge. The closer the field lines are, the stronger the field. This is a radial field. If field lines are parallel, however, the field strength is the same everywhere. We then call this a uniform field. If you draw the gravitational field lines in the room you're in now, they'll appear pretty much parallel. So we can say that on a small scale, gravitational fields are uniform. As electric fields can also repel objects, for consistency, we say electric field lines always show the direction of force on a positive charge placed in the field. That means that around a positive sphere, say a Van de Graaff generator for example, the field lines point away from it, as a positive charge would be repelled if you put it in the field produced by the positive sphere. If you put a negative charge in there, it would be attracted to the sphere. For a radial field, gravitational field strength is proportional to the mass creating the field and inversely proportional to the distance from its center squared. The constant we need to turn it into an equation we call the universal gravitational constant, big G. This is 6.67 times 10 to the minus 11. We give electric field strength the symbol capital E. Don't get it confused with energy. The constant here is 1 over 4 pi epsilon 0. Epsilon 0 being the permittivity of free space, which you'll find on your formula sheet. However, calculating 1 over 4 pi epsilon 0 gives us 8.99 times 10 to the 9. So we can just say that this constant altogether is 9 times 10 to the 9 as a shortcut. We can just call it K. It's very handy and you'll get the correct answer if you use this, and it saves a lot of time and hassle. So I'll be using it from here on out. We can draw the inverse square relationship for G and R on a graph, but for a planet, G, field strength, is at a maximum at the surface. If you dig downward towards the center of the Earth, G decreases linearly to 0 at the center. We can prove this actually. We know G is proportional to m over r squared. Density, however, is proportional to m over r cubed, as is equal to mass over volume. That means G is proportional to rho r. If rho is constant, which we're going to assume it is inside of our planet, G is just proportional to r, hence our linear relationship inside the planet. If you think about it, it makes sense because if you're at the center of the Earth, you'll be pulled in all directions equally, so there would be no overall field or force. This proportional relationship is also useful when comparing field strengths on the surface of planets with different sizes and densities. Field strength, much like force, is a vector. Quite often you'll be presented with two planets and you'll be asked to find out where there would be no overall force or field in between them. In that case, we say G1 equals G2 for the two planets. Again, we're just looking at the magnitudes. That means big GM1 over R1 squared equals GM2 over R2 squared. You could also be given the overall distance D instead. In this case, we replace R2, say, with D minus R1 and then rearrange it to finish it off. As G has the units newtons per kilogram and electric field strength is newtons per coulomb, to find the actual force a field exerts on an object, we only need to multiply by the mass or charge that we're actually putting in the field. So F equals big GMM over R squared. You might say M1, M2 instead. You might use D as well. This is Newton's law of gravitation. For electric fields, F equals KQQ over R squared. This is Coulomb's law. Remember, r must be the distance between the center of the two objects. You could be asked to define these two laws using your words. We can just use the equation, just take out the actual SI units. You know that F equals mg for gravity, as it's the same thing as weight. But it's also F equals ma as well, isn't it? Because we know that gravitational field strength is also the same as acceleration due to gravity. For electric fields, F equals eq. This is a very simple equation that's always used, but it's one people often forget. You know that work done is equal to force times distance, that's Fr in this case. Therefore, if an object is pulled away from an object that's attracting it, like a rocket putting a satellite in orbit, then it must have gained potential energy. This means GPE is equal to GMM over R, and electric potential energy KQQ over R. Now you might say, oh, but I thought GPE was equal to MGH. Well, that's only if the field strength stays the same. If you're in a uniform gravitational field. Like we said, on a small scale, we can say that's true, but not when we're looking at the big picture. Much like we've seen newtons and newtons per kilogram, we have joules, so now we need joules per kilogram as well. This is called potential, symbol V. The definition is this: the work required to move unit mass from infinity to that point. The reason we use infinity as our baseline is because that's the only thing that's common to every object in the universe. So we say that's where you have a potential of 0. As an object gets closer to a planet, the potential gets more negative. Potential is a scalar, so it's the same in all directions. That means we can draw equipotentials around a planet, dotted lines that show certain potentials, much like contours on a map. No work is required to move an object along an equipotential. That's why satellites will orbit a planet without any help. Electric potential is measured in joules per coulomb instead, of course, and we just replace unit mass with unit positive charge. For gravitational potential, V equals minus Gm over R. Electric potential, V equals just kq over r. No minus is needed, because if we have an attractive field, as if it were like a planet, well, we know that it must be a negative charge creating this field, because it has to be attractive to a positive charge. Of course, if it's a positive charge creating a field instead, you'll end up with positive potentials. Gravitational potential can only ever be zero at infinity, whereas electric potential can be zero between oppositely charged objects. As it's a scalar, you just sum the individual potentials at a point to find the overall potential there. Just remember that between two like charges, field strength can be zero, but potential will not be. Speed is proportional to m over r, and density is proportional to m over r cubed. V is proportional to rho r squared. If you have a graph of V against R, there are two things we can do with it. We can read off 2 points, calculate the change in potential in joules per kilogram or joules per coulomb, then multiply by the mass or charge of the object we're actually moving to find the energy or work done. So that means change in potential energy is equal to m delta V or q delta V. You might be tempted to put the distance moved as r in our equation, but remember r is always the distance from the center of the mass or charge that's producing the field. That means if we want to calculate change in potential, instead of using a graph, we must do kq over r1 minus kq over r2. Of course, you can then factorize this. However, if you find the gradient of a potential distance graph with a tangent, this is equal to the field strength at that point. That's because going full circle with our equations, you can see that V over R gives us the equations for field strength. That's why the alternative name for field strength is potential gradient. We can also find it by just doing delta V over delta R if we've been given two potentials and the distance between them. It's not super accurate though. You make a uniform electric field if you have two charged parallel plates. The field lines are parallel and go from the positive plate to the negative plate. Again, the field strength is the same everywhere. If you put an electron in here, for example, it will accelerate toward the positive plate with a constant acceleration because the field strength is constant. For any field, equipotentials cross the field lines at 90 degrees. So that means here they run perpendicular to the field lines. As these equipotentials are equally spaced, that again shows that the field strength is the same everywhere. We know that electric potential is measured in joules per coulomb, energy divided by charge. That means that if we take delta V over delta R and just replace them with the voltage, PD, between the two plates and the separation of the two plates for R, we find that the electric field strength is just equal to V over D, the voltage divided by separation of the plates. If a charged particle enters the field at a right angle, its trajectory is parabolic, and then it's just identical to a normal projectile motion question. You use suvat for one component of its velocity, and your speed equals distance over time for the other component, as that doesn't change. So A equals EQ over M, or VQ over MD. If our parallel plates are making an object levitate, like in Millikan's oil drop experiment, we can say the force due to gravity and the force due to the electric field are equal and opposite, so mg equals EQ. How T or R specifically change, you merely divide one power by the one on the other. Also, you should know that the speed increases as V equals root gm over r, and therefore its kinetic energy increases too. A satellite in a geosynchronous or geostationary orbit has a time period that's the same as that of the Earth's rotation, 24 hours. Quite often you'll have to put this into an equation, but it must be in seconds, so multiply by 3,600. The only place it can stay above the same point on the Earth is at the equator. That means there's a ring of satellites at the same height above the equator. These are used for communication, GPS, television, and internet. A low polar orbit is one which is lower, and according to Kepler's law, it must have a shorter time period. They don't stay above the same point as they move from pole to pole, sweeping out different parts of the Earth as it rotates underneath. These are used for surveillance and weather tracking. Just be careful, if you're given the height of a satellite's orbit above the surface, you need to add on the radius of the planet to get the proper R. You can sometimes be asked the question, how fast would the Earth need to spin for you to appear weightless? In that case, you've just turned into a satellite, and your R is the same as the Earth's radius. All we do is use m omega squared r again. We just do exactly the same thing as we've done before. If you want to escape a gravitational field, you must be given enough kinetic energy at the surface to be equal to the potential energy needed to get to infinity. That means half mv squared equals gmm over r, where v is the escape velocity, the velocity you need to fire something at from the surface, and r is the planet's radius. The little m's cancel, and we get v equals root 2gm over r. So that goes to show it doesn't matter how heavy or light objects are, they all must have the same escape velocity to escape the gravitational field. Distance of closest approach is the same idea but in reverse for an electric field. If you have a positively charged particle moving toward another, it will be repelled. If moving directly toward it, the minimum distance it gets to before turning around and coming back the same way it came is called the distance of closest approach. At this point, it has a speed of 0. Kind of like when you throw a ball up in the air and it reaches the apex. So again, Ke equals Pe. So half mv squared equals kqq over r, where r is our distance of closest approach. A capacitor is a device that stores charge and therefore energy if a PD is applied across it. Double V and Q doubles, so they are proportional. The gradient of this graph is the capacitance of the capacitor, which tells you how many coulombs of charge are stored per volt. This has the unit farad. The equation is therefore Q equals Vc. As energy is charge times voltage, that means the area under the graph gives us the energy stored in the capacitor. As it's a triangle, the equation is E equals half QV. Substituting out Q or V with our first equation, we get the alternatives half CV squared and half Q squared over C. You don't really measure charge directly, which is why we have to calculate it using charge equals current times time. But this only works, however, if the charging current is constant. As the current will start high and fall to 0 if we just hook up the capacitor to a battery, we need a variable resistor that we're constantly changing in order to keep the current constant. Once fully charged, the PD across the capacitor will be the same as that of the battery. It's worth remembering that before this point, the rest of the PD from the battery will be taken up by the resistor in the circuit. When discharging a capacitor, usually through a resistor, the PD decreases or decays exponentially, similar to nuclear decay. The equation is this: V over V0 equals e to the minus t over RC, where V is the PD at time t now, and V0 is the initial PD. You might see it as V equals V0, etc., but this way you can see that it's just a ratio which will be between 0 and 1. How much of the initial voltage do we have left? It also works for current I and charge Q as well. Thinking about it being a ratio makes it easier to rejig this for charging instead. We just want the other proportion, so it's equal to 1 minus e to the minus t over RC, where V0 is the maximum final PD when fully charged in this case. Once again, this works for charge, but current still decays when charging. It doesn't increase, it decreases, which makes sense, doesn't it? To rearrange for t, r, or c, we natural log both sides, leaving us with log or ln on the left. Yes, I can say that even though it's a natural log. Log v over v0 equals minus t over rc. This is needed when doing an experiment to find an unknown capacitance. We measure v as it changes with time as it discharges. Then we can either do a graph of minus log v over v0 against t, and the gradient will be 1 over rc, or we can use our log identities to say that log v over v0 is equal to log v minus log v0. We plot log v against time, and again the magnitude of the gradient is equal to 1 over rc. We use half-life to compare radioactive isotopes, but for capacitors we use the time constant. This is the time it takes such that the fraction of PD left is e to the minus 1, which is equal to 0.37, 37%. That can only be true when the time t is equal to RC. So t over RC is equal to 1. So the resistance times capacitance is equal to the time constant. If you're not in a rush, try and prove that the units check out. If you're given a decay graph, you find 37% of an initial value. It doesn't matter where you start actually, but the time it takes to do that is the time constant, and that's equal to RC. The basic structure of a capacitor is two parallel plates which become oppositely charged when a PD is applied. Remember, no charge should flow directly between the plates. In reality, these plates or foils are wound into cylinders, as you probably see from the designs of the ones you use in your school lab. Capacitance is proportional to the area of these plates and inversely proportional to their separation. The constant that makes this an equation is permittivity, epsilon. This in essence is a measure of how easy it is for an electric field to be produced in the space between. If there's air or a vacuum between this, it's the permittivity of free space, epsilon 0. You're given the value in your formula sheet. If there's anything else in between, the permittivity will be greater than that of free space. So we say that the permittivity is equal to that of free space times the relative permittivity of the material, which is just a number that's greater than 1. If it's 2, then that means it's twice as good as free space. We can increase the capacitance by inserting a dielectric between the plates, an insulating material that contains polar molecules. That is, they're affected by electric fields. We can represent them with just a little peanut shape with a delta plus and delta minus to show that they line up along these field lines. As a result, the edges of the dielectric will become charged oppositely to the plate it's nearest to. What's also happening is that these polar molecules are producing their own counter-electric field, therefore reducing the overall electric field between the plates and therefore lowering the PD needed to store the same charge. If you change any aspect of a capacitor, A, D, or epsilon R, you can be asked what the knock-on effects are for V, C, Q, or energy. First, you need to know if the capacitor is still connected to the battery or not. If it is, V will stay constant and Q will change. If it's disconnected, Q is constant and V changes instead. It's a bit more complicated with energy as we have three equations to choose from. You choose one that has a constant in it, so if disconnected we choose E equals half Q squared over C. This example here can also be explained in terms of electrostatic potential energy. Like we said, the edges of the dielectric are charged oppositely to the plates, which means they're attracted to them. To remove the dielectric, we must therefore do work to separate them. You have to put in energy. Where does that energy go? Into the capacitor. Upthrust is the force that pushes upward on an object in a fluid. This is due to the fact that the object displaces the same volume of liquid. That means the upthrust is equal to the weight of the fluid displaced. So U equals m times g, and m is equal to rho v, density of the fluid times the volume of the object. Of course, the weight of the object also pulls downward, so the resultant force is one minus the other, which can then be used in Newton's second law. If the object is moving, however, there will be drag pushing in the opposite direction to its velocity, which also must be taken into consideration when finding the resultant force. Forces can also deform an object. If you pull on a spring that is fixed at one end, it will stretch or extend. Hooke's law states that F equals Ke, or K delta L, or Kx. That's force equals spring constant, sometimes called stiffness, times extension. The unit for spring constant is newtons per meter, at least it is if extension is in meters. This works for any object that stretches elastically, that is, returns to its original shape and length once the force is removed. It can also be true if an object is compressed instead. The area under the graph gives you the work done on the spring and therefore the elastic potential energy stored in the spring. If you attach two springs end to end, we might say in series, they stretch twice as far with the same force, meaning the equivalent spring constant must be half what it is for one of the springs. Side by side, in parallel, and the opposite is true. Even if not a spring, materials can still be stretched or compressed. They can be deformed with a force. Stress is basically pressure, it's force per unit area, so newtons per meter squared, also called pascals. Strain is just a ratio of extension to original length. Drawing a graph of stress against strain will likely give you a proportional relationship, at least to begin with. The gradient of this graph gives us the Young modulus, which is unique to every material. As strain doesn't have a unit, the Young modulus is also measured in pascals. Replacing stress and strain with their own equations, the full version of the equation for E is FL over A delta L, or X or E, depending on what you use for your extension. Area is proportional to d squared, as area is equal to pi d squared over 4. That means if you double the diameter, the extension quarters. Add even more force, and the graph will start to curve though. We've gone past the limit of proportionality. We can't use Young's modulus past this point. However, even after it curves, if we remove the force, it can still return to its original length. It can still behave elastically. We say the unloading curve might look different to the loading curve. If we make a graph of force against extension, the area under the loading curve is still the energy needed to stretch the material, just like with springs. The area under the unloading curve, however, is the energy that you get out as it's returning to its original length. That means that the area enclosed between the two is the energy lost in this process, usually as heat. Increase the force even more and it won't return to its original length. We've gone past the elastic limit. It's now undergoing plastic deformation instead of elastic. The highest point of the curve is called the ultimate tensile strength. The line can go down after this point as the wire or cable or whatever starts to neck. It carries on extending even if you remove some of the force. A ductile material like copper will have a large plastic region, whereas a brittle material generally has a high Young modulus and suddenly snaps. Simple harmonic motion describes the motion of any object that is oscillating around a point like a pendulum or a mass on a spring. There are two conditions. The acceleration must be proportional to the object's displacement from equilibrium, and it must also be in the opposite direction to the displacement. What's true for acceleration is also true for the force, the restoring force, that's trying to get it back to equilibrium. The equation A equals minus omega squared x shows both of these conditions. As we know from circular motion, omega is equal to 2 pi f, well 2 pi over t, and x is the displacement from equilibrium in meters. If we use calculus in A-level physics, we can derive this from the other equation you'll see in a minute. But as we usually don't, we just use this equation as our jumping off point for SHM. In calculations, we're never really concerned with the minus, as we know it's going to change from negative to positive as it oscillates. Maximum acceleration occurs at the maximum displacement, which you know is the amplitude, capital A. So little a max equals omega squared big A. We've just swapped out displacement for amplitude. If you draw a graph to show how displacement changes with time for something undergoing SHM, like a pendulum, we end up with a sine graph. To be clear, it's a sine graph if we start at 0, it's cos if we start at amplitude. Still sinusoidal, just shifted 90 degrees. At any given time, the displacement is equal to a fraction of the amplitude. This fraction is given by sine or cos omega t. Be careful when using S or cos with any periodic motion like circular or SHM, because your calculator must be in radian mode. The full equation for velocity at any point is this. Luckily, it's fairly unlikely you'll have to use this, as more often than not, we're just concerned with the maximum velocity, which has to be at equilibrium. That's where x equals 0. So that means Vmax equals omega A, or 2 pi Fa. This is an important equation because it allows us to find the maximum kinetic energy if we use this speed in half mv squared, and the maximum kinetic energy is equal to the total energy of the system. Going back to our graph real quick, this is essentially distance over time. So if you're asked to find the maximum speed from it, you could draw a tangent at equilibrium and you'll get the maximum gradient, which is then equal to the maximum speed. But a far more accurate method is to get the time period and amplitude from the graph, then calculate Vmax equals 2 pi Fa, or 2 pi over t times A. As the object moves away from equilibrium, kinetic energy is turned into potential energy. In the case of a pendulum, that's gravitational potential energy. Be careful with displacement for a pendulum though. The displacement is roughly a straight line from equilibrium to where it is. It's not the vertical height it's moved. That means if you are given the maximum height of a pendulum, the only thing you can do is find out the GPE it has at amplitude, then equate this to the kinetic energy it has at equilibrium to find Vmax. Height is not displacement or amplitude for a pendulum. You can then find out more about the oscillations using Vmax equals 2 pi Fa as before. If there's no damping or resonance and it's a closed system, no energy should be lost to the surroundings, which means the total energy stays the same as kinetic energy and potential energy do their balancing act. For a pendulum, time period is equal to 2 pi root L over G, where L is the length of the string, to be precise, from the pivot to the center of the bob, and G is gravitational field strength. Note there's no mass in this. It doesn't affect the time period, or therefore the frequency either. For a spring, T equals 2 pi root M over K, where K is the spring constant, M is the mass. These equations often crop up in proportionality multiple choice questions. For example, what would happen to the frequency of a pendulum if you doubled the length? Well, the time period would go up by a factor of root 2, which means the frequency would do the opposite. The pendulum equation is a slight approximation though, as it assumes the motion is along a straight line, which is why if we measure the time for 10 oscillations in an experiment and divide by 10 to get an accurate time period, for example, we must use a small angle, say less than 10 degrees. Use a large angle and the model breaks down. A pendulum's motion isn't circular motion, apart from when it passes through equilibrium. It is that for a brief moment. This allows us to use Vmax from SHM and use it in our circular motion equation, F equals mv squared over r. And that gives us a centripetal force, which is going to be the tension in the string minus the weight, again, if we're thinking about magnitudes. In reality, there are resistive forces like air resistance that oppose the motion of the object moving. It always acts in the opposite direction to the velocity. We call this a damping force. It removes energy from the system. If we draw what happens to oscillations over time, we can see that the amplitude decreases gradually. This is what we call light damping. Sometimes you'll see a line that joins the peaks together, which shows us exactly how the amplitude is changing over time. You could be asked to state how much energy is left at a certain time. In that case, just remember that Vmax is proportional to the amplitude and energy is proportional to V squared. So that means the energy of the system is proportional to amplitude squared. So if the amplitude is halved, that means the energy will have quartered. If the resistive force is a lot larger, the object won't even get a chance to oscillate. Its displacement will just gradually decrease. This is like if you grab someone on a swing to let them down slowly. We call this heavy damping or over damping. Critical damping is when the damping force is applied just as the object reaches equilibrium, ensuring that it comes to a stop at equilibrium as quickly as possible. This would be like you grabbing somebody on a swing as they reach the bottom. Shock absorbers in car suspension are designed to do this as much as possible. So when the wheels move upward when going over a bump, they go straight back down to where they're supposed to be, so the car is affected as little as possible. Resonance is the opposite. It's when an external force is driving the oscillations, increasing the amplitude, adding energy into the system. But we do have to add the caveat that this only happens when a system is lightly damped. Maximum resonance occurs when the frequency of the driving force, the driving oscillations, matches that of the natural or resonant frequency of the system. That's the frequency it would oscillate at without the driving force. The driving force frequency can also be a multiple of the natural frequency, and you'll still get substantial resonance. The driving force and the restoring force are 90 degrees out of phase with each other, which means the driving force pushes most when the object is at equilibrium, much like the wheel under a swinging pirate ship ride, pushing it higher and higher every swing. If you draw a graph of amplitude against driving frequency f, we get the highest amplitude, the most resonance, when it's equal to the natural or resonant frequency f0, as we know. If you add more damping, though, the height of that peak decreases as you reduce the effect of resonance. Note that the peak does not get any narrower, though. All waves transfer energy without transferring matter. Longitudinal waves are those in which the direction of oscillations is parallel to the direction of energy transfer, that is, the direction the wave is going. In these waves, particles bunch up, we call these compressions, and then they spread out, we call these rarefactions. Transverse waves are those in which the direction of oscillations is perpendicular to the direction of energy transfer. We can represent any wave, including longitudinal waves, with a waveform. Displacement is at the y-axis. Basically, that just means how far the particles have oscillated away from their original position, and it can be either distance or time on the x-axis. The peak of a wave is called the amplitude. It's the maximum displacement from equilibrium. If it's distance on the x-axis, one complete wave here gives you the wavelength. We give this the symbol lambda for short, but it's measured in meters. If it's time on the x-axis instead, one complete wave now gives you the time period. This is the time it takes for one complete wave to pass. Frequency, on the other hand, is how many waves pass a point every second, and the unit is hertz. Frequency is equal to 1 divided by time period, f equals 1 over t. The wave equation is this: v equals f lambda, or you might see c equals f lambda. That's wave speed equals frequency times wavelength. It's worth remembering that visible light wavelengths vary from around 400 to 750 nanometers, with red light having the longest wavelength and blue light having the shortest. The intensity of a wave is proportional to the amplitude squared. That means that if the amplitude doubles, the intensity quadruples. When light waves move from one medium to another, say from air to glass, they change speed. In this case, the wave slows down and the wavelength also decreases. A change in medium also results in a change in direction. This is called refraction. That is, if it's at an angle to the normal, the line we draw perpendicular to the surface. If light slows down, it moves closer to the normal, so that means the angle of refraction is smaller than the angle of incidence. How much a medium refracts light is determined by its refractive index, symbol n. It's just a ratio that's equal to the speed of light in a vacuum, basically the same for air, divided by the speed of light in the medium. So it will always be a number that's greater than 1. If you calculate sine I over sine r for a light ray entering a medium from air, this gives you the refractive index. The full equation for refraction is Snell's law though. n1 sine theta 1 equals n2 sine theta 2. You can see that we've just replaced I and r with thetas. Bear in mind that in reality the refractive index of a material varies with wavelength. Blue light's refractive index will always be higher than red light's. That means that blue light refracts more than red. That's why white light undergoes dispersion when it passes through a prism. Let's say the light ray is coming out of the glass block and into air. Now, if we keep increasing this angle of incidence, eventually we'll end up with an angle of refraction of 90 degrees. We can think of the light ray as going along the boundary. But when we reach this point, we can say the angle of incidence is now equal to what we call the critical angle, and that's going to be different for every medium. If we make the angle of incidence even bigger than the critical angle, that means that no light is going to be refracted out of the block. Instead, all light is reflected back inside. By the way, we always get some reflection, a partial reflection when we have refraction, but now we have total internal reflection, TIR. Want to calculate the critical angle? Well, you can start with Snell's law. You call theta 1 theta c instead, make n2 1, and we end up with sine theta c equals n2 over n1. This, incidentally, is how optic fibers or fiber optics work. The basic optic fiber is a glass core surrounded by a protective sheath. The issue is that the sheath will have a higher refractive index than the core, so TIR would not happen if it wasn't for the extra layer called the cladding that's between the two. It has a lower refractive index than the core, so TIR can occur when the light reaches the boundary between them. One of the issues with optic fibers is that, in fact, light will diverge, spread out as it travels down it. That means rays can take different paths and therefore different times to reach the other end. This is called modal or multipath dispersion, and it results in pulse broadening. If pulses are stretched too much, they start to overlap as the next one has started to arrive before the first one has completed its journey. Your data is a goner. To mitigate this, we can do a few things. Number one, make the fiber really thin. The thinner it is, the less light will diverge. Number two, put repeaters in every so often to retransmit the slightly broadened pulses as brand new ones. Final clever thing to do is use graded index fibers. Lenses are curved blocks of glass that refract light to focus it. Also, the lenses in your eye do the same job. They make light rays converge, meet, or diverge, spread out. A convex lens can make rays converge. This is the symbol we use to represent it. If rays enter parallel to what we call the principal axis, for example, light rays from a very distant object, the lens will make the rays converge at this point here. This is called the principal focus. The distance from the center of the lens to this point is called the focal length. This doesn't change for a lens, and we can draw it on both sides, and you'll see why in a second. However, light doesn't usually come from objects infinitely far away, but from objects a little bit nearer. The object could be anything, but we often represent it with just an arrow. A convex lens can then project an image using the light that comes from the object, but we only consider the light coming from the top of the object. And we can do that by drawing two rays. One always goes straight through the center of the lens, and one goes parallel into the lens, then through the principal focus. Where these two rays meet is where the image will be formed. That's where you want your projector screen or retina or camera sensor or whatever to be in order to get a clear image formed. You'll also notice that the image is smaller than the object here, so we say it's diminished. It's also upside down, so we say it's inverted. Things get a bit trickier when the object is close to the lens. Now the rays don't meet. The image can't be projected. However, if we extrapolate the two rays back behind the lens, they do meet. We can draw the image here, and we can say that it's magnified, it's upright, but it's virtual. That means that it can't be projected. It's no longer a real image like we had before. This would be what a magnifying glass does, for example. Your eye can then deal with this diverging light accordingly to make it focus on your retina, but that means you see this magnified virtual image, so things appear bigger. Concave lenses always diverge light. They always produce a virtual image. With these, our line parallel in goes back through the other principal focus behind the lens. Where it meets the other ray is where the virtual image is. This image is also diminished and upright, as you can see. The power of a lens is just the reciprocal of focal length. We give it the unit diopter, d. The total power of multiple thin lenses used together is just equal to the sum of their individual powers. And the lens equation is this: 1 over u plus 1 over v equals 1 over f. Light emitted from the sun oscillates in all orientations. However, if you have a polarizing filter made of very small lines, it only lets half of the light through. Only half is transmitted. This is because it only lets waves of certain orientations through. We say that if the lines are vertical, waves oscillating vertically are absorbed, while horizontally oriented waves are transmitted, pass through, and vice versa. Now, some people get frustrated with this because they're taught the picket fence model of polarization. But that's not how it works. This is proven by the fact that if you have a vertical microwave transmitter, the receiver must also be vertical in order to receive them. Waves between vertical and horizontal are transmitted or absorbed according to their angle. It's very complicated in reality, but put simply, the light is now polarized and the intensity of the light is halved. Put another polarizing filter at 90 degrees behind the first one and all of the light is absorbed. A normal light wave is what we call a progressive wave. The wave moves while the medium or particles just oscillate around a point, say up and down. 2 points, 1 wave apart, are said to be in phase. They're doing the same thing at any given time. We say their phase difference is 0, or we might say 360 degrees, as we can represent wave cycles as circles. We can also split circles and therefore cycles into radians instead of degrees. There are 2 pi radians in a circle. The phase difference of these 2 points is 2 pi radians. Like we said, that's the same thing as 0. Points on opposite sides of a wave are completely out of phase, or we might say they're in antiphase. They're half a wave out of phase, so their phase difference is 180 degrees or pi radians. These 2 points are a quarter of a wave out of phase, so that's a phase difference of 90 degrees or pi over 2 radians. We generally don't give phase differences above 180 degrees pi radians, as we can just give the opposite phase difference. So 270 degrees is just given as 90 degrees, etc. It's just a difference after all. Any phase difference can be calculated as a fraction times the total in a cycle. So we can do the distance between 2 points divided by the wavelength, or time difference between 2 points divided by the time period, depending on what graph we're given. Then we just multiply by 360 or 2 pi, depending on whether we want the phase difference in degrees or radians. When two progressive waves traveling in opposite directions meet, they undergo superpositioning. They are superposed. That means their displacements are summed at every point. So you'll no longer see the original waves, you'll just see the resultant wave of these two waves meeting. When these waves have identical frequency and wavelength, a stationary wave is formed. The point at which the resulting wave doesn't move is called a node. That's because the displacements are always summed to 0 at these points. We call this destructive interference, so the amplitude is 0 at this point. At a node, no energy is transferred. At all other points, the resulting wave will oscillate due to constructive interference. Where the amplitude is at a maximum, these are called antinodes. We can see this if we attach a string under tension to a vibration generator. The wave is sent down the string, it reflects at the pulley, goes back the other way, and then these two waves interfere, superpose. The simplest stationary wave looks like this. We call this the first harmonic, or the fundamental mode. One loop, one antinode, and a node at both ends. We have half a wavelength on the string, so that means L equals lambda over 2. The frequency of this first harmonic is given by the equation F equals 1 over 2L, length of the string, times root T over mu, T being the tension in newtons, which is usually the weight of the masses hanging on the end, and mu being the mass per unit length of the string, so that's in kilograms per meter. Incidentally, root T over mu actually gives you the wave speed. Double this fundamental frequency and we get the second harmonic, L equals lambda in this case. Third harmonic, L equals 1.5 lambda, and so on. Stationary waves can also be formed in tubes of air. At a closed end, a node must be formed. At an open end, an antinode. We can represent the stationary wave much like we do for a string. Just bear in mind that the first harmonic is likely to be different than that of the string because one or two of the ends are probably going to be open. Unlike progressive waves, points on stationary waves can only ever be completely in phase or completely out of phase. It just depends on whether or not they're the same side of equilibrium. That's because 2 points above equilibrium will reach their own different amplitude at the same time, and they'll both reach equilibrium at the same time too. Even if waves aren't traveling in opposite directions, they can still interfere when they meet. Thomas Young put a thin slit next to a candle to first ensure that the light used for the experiment was coherent. That means it has a constant phase difference, basically just means it's in phase. This light then passes through a double slit. The result was bright and dark fringes appearing on the screen. We call these maxima and minima. We have a central maximum because these two rays meeting have traveled the same distance, so therefore they interfere constructively. The dark fringes or minima are due to the light from the two slits traveling slightly different distances to each other. The dark fringes or minima next to the central maximum are due to the light from the two slits traveling slightly different distances. We say their path difference is half lambda. That means they arrived 180 degrees, completely out of phase, and interfered destructively, cancelling each other out. The first bright fringe from the central fringe is a result of the path difference being the same as the wavelength, lambda. That means that they arrive in phase, interfering constructively, resulting in a bright fringe. The next dark fringe is a result of the path difference being 1.5 lambda, and so on. Young's double slit equation is W equals lambda d over S, where W is the fringe spacing. That's the distance between the center of two bright fringes or two dark fringes. D is the slit to screen distance, and S is the slit separation. Note that this is not slit width. That really doesn't change anything. However, this equation is an approximation, and it can only be used when the screen distance is much larger than the slit separation. That's why the equation is likely to break down if we use sound instead. If you have two speakers producing the same waves in phase, you walk at right angles to them, you'll hear the volume fluctuate as you go through maxima and minima. We can represent the pattern by drawing a graph of intensity against distance from the central max. The intensity falls away gradually and they all have the same spacing, but light can also diffract when you just use a single slit. As diffraction happens at both edges of the slit, it gives this diffraction pattern instead. The two differences being that the intensity falls away much quicker and the central max is double the width of the subsequent fringes. Don't forget that if you do this experiment, it's always more accurate to measure 10 fringes than divide by 10 to get W. And again, when we do it, we probably use a laser as it provides coherent light that's also monochromatic. Just one wavelength is emitted, resulting in clearly defined fringes. However, using a candle that emits a spectrum of wavelengths, as Young did, he saw the white light splitting into different colors. As red light has the longest wavelength, it diffracts the most, so it can be seen on the outside edge of the fringes. Blue light has the shortest wavelength, so it diffracts the least, so it can be seen on the inside edges of the fringes. If you replace the double slit with a grating of very small lines separated by line spacing little d, you only get constructive interference at a few points very far away from the central max. We call these orders now instead of fringes. The central max is the 0th order. As we're dealing with large angles, we don't use Young's double slit equation here. So we use the more accurate equation, n lambda equals d sine theta. Often you'll be given the grating or line spacing in lines per millimeter, which you need to turn into meters. Essentially meters per line is the reciprocal before it can go into the equation. You can also be asked to find out the maximum visible order. In this case, we want to find out what order is made at 90 degrees. Sine theta equals 1, so n equals d over lambda. Let's say this ends up being 3.8. There's no such thing as a 3.8th order, so only orders up to the third one are visible. Also, they might try to catch you out by asking how many orders will be visible, rather than what is the highest order. In this case, you have to count the orders on both sides, including the 0th order, so in this case that will be 7. Very cheeky. Just be careful with some multiple choice questions involved in this equation. You might get asked what will happen to the orders if the wavelength is halved, say. In this case, you don't look at theta at all, as it's not proportional to anything in the equation. Instead, we say n is inversely proportional to lambda. If lambda halves, n doubles. That means that what was the first order is now the second order, and a new first order is created between it and the 0th order. If d is changed instead, we say n is proportional to d. Electrons in an atom orbit the nucleus at specific or discrete energy levels. N1 being the lowest energy level, or ground state we can call it, then N2, N3, etc. An electron can be excited or raised to a higher energy level either by another free electron colliding with it, giving it some of its energy, or by it absorbing a photon. However, in this case, the energy of the photon must match the difference in energy levels exactly, otherwise it will just pass through. Either way, after it's been excited, the electron will pretty much immediately fall back down to its ground state, emitting photons in the process. We call this de-excitation. But it can take different routes down. From N3, for example, it can either go straight down to N1, or it can go to N2 first, then down to N1. This means there are 3 possible wavelengths or frequencies of photons that could be emitted when it de-excites. From N4, there are 6 different possible wavelengths. The energy of each photon is equal to hf, so the bigger the drop, the higher the frequency of photon emitted, and the shorter the wavelength is, of course. If the incoming or incident free electron or photon has enough energy, however, the electron can reach the ionization level, which then means it's able to leave the atom, leaving behind a positively charged ion. The energy levels can be given in joules or electron volts. 1 electron volt is equal to 1.6 times 10 to the minus 19 joules, which should look familiar as it's the same as the charge of an electron. So to convert joules to electron volts and vice versa, just think, do I want a smaller number or a bigger number? You always want a very small number of joules and a normalish number of electron volts. After all, that's why the unit is so handy. Sometimes mega electron volts are even better. You can convert joules to electron volts and then you use your conversion factor of 1,000,000 10 to the power of 6 to get to mega electron volts, but I guarantee it's more helpful to remember that to go from joules to mega electron volts, the conversion factor is 1.6 times 10 to the minus 13 instead of minus 19. An emission spectrum is just a diagram that shows the various wavelengths of photons that are emitted by an object, for example, a star. As different atoms or molecules have specific energy levels, we can tell what particles are found in that star. And then we can also see how redshifted these wavelengths are too, which we can then use to determine the recessional speed of galaxies, for example. An absorption spectrum is obtained when we emit all wavelengths of light through a gas or plasma, that's just an ionized gas, and detect what wavelengths are not transmitted, therefore absorbed. These absorbed wavelengths are represented by black lines on the spectrum. Fluorescent tube lights, strip lights, consist of a cathode and anode that cause electrons to be accelerated through the low-pressure mercury gas inside. An electron will collide with a mercury atom's electron, exciting it to a higher energy level. When it de-excites, it emits a UV photon. That's not useful for our eyes, so it needs to be absorbed by the fluorescent coating on the inside surface of the tube. It raises one of the electrons in the coating to a higher energy level, and then it de-excites via multiple levels, emitting lower frequency visible photons instead. We say photons have wave-particle duality. The photoelectric effect is the main piece of evidence that light acts like a particle. Shine light on certain metals and electrons will be liberated from the surface. They pop off, as they've absorbed the energy as kinetic energy. How can we tell? Well, if we have the metal in an evacuated tube in a circuit with an ammeter, a tiny current will start to flow as the electrons cross the gap. Add a variable PD into the circuit, and we can oppose this current until it reaches zero. We call this potential needed the stopping potential, Vs. We therefore say at this point the kinetic energy of an electron would have to equal QV, or EV, as it's an electron. Bear in mind, this technically gives the maximum kinetic energy an electron has after liberation, as most electrons will have less energy due to them not being right on top of the surface of the metal. We vary the frequency of this incident light and plot the EK max against this, and we end up with a straight line. The gradient is where Planck's constant comes from. It doesn't go through the origin though, which means that the electron is not gaining as much Ke as the photon's energy going in. It's lost some in the process of being liberated. Extrapolating this line back, and we get this energy which we call the work function. This is the minimum energy required for an electron to be liberated from the surface of a metal. Think of it as an energy toll the electron must pay to escape. The minimum frequency needed to liberate an electron we call the threshold frequency, F0. This means that the work function is therefore equal to h times F0. So here's the full equation. Ek max equals hf minus phi. The kinetic energy the electron has left over equals the photon energy going in minus the work function, the energy toll. This proves the particle theory of light, because if the frequency of light isn't high enough, electrons won't be liberated no matter how intense or bright the light. This shows that one photon is absorbed by one electron. We say it's one-to-one interactions, and that requires photons to be discrete packets of energy. So, light acts like a particle, but any particle can also act like a wave. If we fire electrons at a graphite target in an evacuated tube, we see rings forming on the phosphorescent screen behind. The only way that this would be possible is if the electrons are diffracting as they pass by the graphite atoms and producing an interference pattern with maxima, bright rings, and minima, dark rings. Electron diffraction is the evidence that particles also have wave nature. More on diffraction in waves, of course. The wavelength of a particle is given by the de Broglie or de Broglie wavelength equation. Lambda equals h, Planck's constant, over mv, or p, the momentum of the particle. Faster speed means smaller wavelength, which means less diffraction, according to n lambda equals d sine theta from waves. Here's the standard graph showing how intensity varies with distance from the center. Note that it doesn't decrease to zero, unlike diffraction patterns for light. At this point, it's worth bringing up the fact that you might have to convert kinetic energy into momentum, or vice versa. The trick is this. We know kinetic energy is equal to half mv squared. Multiply both sides by m, and that gives m times e equals half m squared v squared, or half times momentum squared. Let me just rearrange for p. This comes in handy especially in multiple choice questions. If you have a block of ice and supply heat to it, its temperature will increase. The particles vibrate faster, which means they're gaining kinetic energy. However, once it reaches the melting point of 0 degrees C, its temperature will remain constant until it's all melted. Only then will its temperature start increasing again. The same thing happens when it reaches 100 degrees and it turns into a gas. But why the constant temperature? After all, energy is still going into the ice, but during a change of state, the particles don't gain kinetic energy, but rather potential energy. An increase in temperature means we must have an increase in kinetic energy of the particles, while a change in state, when heating anyway, must mean an increase in potential energy. During a change of state, the temperature stays constant, so we can't use the specific heat capacity equation. Instead, we use the SLH, specific latent heat equation. SLH of a substance tells you how much energy is needed to change the state of 1 kilogram of it. You probably know all of this from GCSE, to be honest, but the questions you can get can be fairly complicated at A-level. For example, you might get two substances at different temperatures touching and they reach a common temperature. In that case, you equate the SHC equations for both, but replace delta T with T minus T1 for the colder substance or object and T2 minus T for the hotter one. Then expand, multiply out, rearrange and factorize to find the common temperature T. If it's an ice cube melting in a drink, for example, you must add on the SHC equation while it's ice and the SLH equation. There are many variations on these questions, so just remember you equate the total energy gained by one object to the total energy lost by the other. The Celsius scale is not an absolute scale, that is, it doesn't start at 0. We know that the higher the temperature, the more kinetic energy the particles have. So we must have a scale that starts at 0 when particles have in theory 0 kinetic energy. That's the Kelvin scale. Same increment as Celsius, just shifted by 273. Minus 273 degrees Celsius is 0 Kelvin. That is absolute 0. Note that it's not degrees Kelvin. To convert degrees C to Kelvin, just add 273. Particles can be cooled to almost absolute 0, but even if you don't have the kit to do this, we can still cool a gas and measure the change in pressure at a constant volume, or change the volume at a constant pressure. Plotting pressure or volume against temperature in degrees Celsius, we end up with a straight line. Extrapolating this to where it meets the x-axis, a pressure of 0 is absolute 0. Doing this by hand isn't very accurate as it's a long extrapolation, so it's better to do this algebraically. You always have to use Kelvin when dealing with calculations involving temperature. The only exception is SHC equations because that's a change in temperature. A change in degrees C is the same as a change in Kelvin. This is Boyle's law. Pressure is inversely proportional to volume at a constant temperature. We call this an isothermal change. Charles's law is this: volume and temperature are proportional at a constant pressure. The pressure law, also known as the Gay-Lussac law, pressure is proportional to temperature at a constant volume. Combining these three laws, we can say that PV is proportional to T. To turn this into an equation, that's big N times K, where big N is the number of gas particles or molecules and K is the Boltzmann constant. As big N is huge and K is tiny, we can swap them out for little n, that's moles, and R, the molar gas constant, or we might just say gas constant, which is 8.31. Much nicer numbers to deal with. If only 2 out of PV and T are being changed, we just use one of the above laws. If all 3 are being changed, and also N isn't changing, then P1V1 over T1 equals P2V2 over T2. We explain gas pressure with the kinetic theory of particles, but our model only works perfectly with a theoretical ideal gas. Some real gases come close, like ironically named perfect gases, but we must make 5 assumptions for an ideal gas, so we can then use our laws. We use the acronym RAVED. R is for random, particles move randomly. We know this from Brownian motion. That is the fact that if you put smoke particles under a microscope, you can see them moving randomly due to air particles colliding with them. A is for attraction, as in there is no attraction between the particles of the gas. V is for volume, as in the volume of the particles is negligible compared to the volume of the container they're in. E is for elastic, all collisions are elastic, and D is for duration. The duration of collisions is negligible compared to the time between collisions. To derive the kinetic theory equation, we imagine a cube of sides Lx, Ly, and Lz. A molecule inside collides with one of the sides, the area Ly, Lz, and it bounces off it. Its change in momentum is minus 2 mu, but we can drop the minus. We know that force equals change in momentum over time, but it's not exerting this force all the time, so we use the time it takes between these collisions. It takes 2 lots of distance divided by speed, so 2Lx over u. Therefore, force is equal to 2mu over 2Lx over u, which gives us mu squared over Lx. Pressure is force divided by area, so dividing by Ly, Lz, we end up with P equals mu squared over all 3 lengths, and so that's the same as mu squared over the volume. As any molecule can travel in 3 dimensions, we can say that u squared is equal to a third CRMS squared. CRMS is the root mean square speed. This is essentially a usable average speed of the particles in a gas. The average velocity is 0, as the particles travel in all directions equally when averaged. And so to calculate URMS, that's just the RMS values in one direction, we add up their squares, divide by the number of molecules, then square root all of this. And so then C is a combination of U, V, and W, the velocities in all 3 dimensions. Multiplying this equation by the number of molecules, big N, gives us the pressure of the whole gas. Rearranging, we can see that PV is equal to a third NmCRMS squared. Remember, m is the mass of one molecule, not the mass of the gas. However, big N times N does give us the total mass of the gas. So that's why we can replace Nm over V with the density of the gas. So P is equal to 1/3 rho C squared. When doing calculations, don't bother writing the RMS. As PV is also equal to nKT, we find that mc squared is equal to 3kT. Half this and we have kinetic energy, half mc squared, half mv squared. So the kinetic energy of one molecule in a gas is equal to 3/2 kT. That means if you know the temperature of a gas, you can automatically know the energy of one molecule. Multiplying by big N, of course, and you have the total kinetic energy of the gas. Notice there is no mass in the equation. That means no matter what particles you have in a gas, say it's air, it has nitrogen, oxygen, carbon dioxide molecules, they all have the same kinetic energy because they're at the same temperature. However, as they do have different masses, they will have different speeds. Of course, you saw what a PV graph looks like for Boyle's law earlier. We can draw an arrow to show whether the gas is being compressed or expanding at a constant temperature. We can also draw what happens to a gas if it's compressed at a constant pressure. Only volume decreases. The area under any line on this graph equals work done. Newtons per meter squared times by meters cubed gives us Newton meters. That's the same thing as joules. Work done. If a gas is being compressed, we say that work is being done on the gas. If it's expanding, we say the gas is doing work. If the pressure is constant, we say that the work done by or on the gas is equal to P delta V. If you have a straight line going down, that's a decrease in pressure at a constant volume, so no work is being done. A, Z, and N are the symbols used for mass number, atomic number, and number of neutrons, respectively. Here's a graph of N against Z. As you can see, isotopes generally sit above the N equals Z line, which means they have more neutrons than protons. The further they are from this curve, the more unstable they are, and the more likely they are to decay to get closer to the curve. Lighter isotopes are generally beta minus emitters. Heavier isotopes are alpha emitters. Beta plus emitters don't exist naturally as they require proton doping to produce the right isotopes, which puts them under the curve. We can zoom in on this graph to show the decay chain an unstable isotope will move through. They can also take different routes to end up at the same stable isotope. There are always diagonal lines in this case, but just be aware that you could get a graph of A against Z instead. In this case, you get a horizontal line for beta as the mass doesn't change. Briefly, metastable states, gamma emitters aren't drawn on this graph because, well, of course, the nucleus doesn't change. What usually happens is that an alpha or beta decay occurs, leaving the nucleus at an excited energy state, much like an electron. It will usually de-excite instantly, emitting a gamma photon then as well. This means it's hard to get a purely gamma-emitting source. However, some isotopes can decay via alpha or beta, then remain at the excited state for a long time after that, before releasing that gamma photon. This is called a metastable state. The example we use is usually molybdenum-99. This decays via beta minus, leaving technetium-99 in a metastable state. This is then filtered from the undecayed molybdenum to then be used as a pure gamma emitter for uses such as medical tracers or radiotherapy. The relative mass of nuclei is based on the relative atomic mass unit U. This is defined as 1/12 the mass of a carbon-12 atom. And we find that neither a proton nor a neutron have a mass of exactly 1 U. Even if a helium nucleus had a mass of exactly 4 U, if you manage to split it up into its constituent nucleons, 2 protons, 2 neutrons, it will end up having a mass of more than 4 U. How's that? Well, it's because it requires work to do that, to separate them out, to overcome the strong nuclear force. This energy is turned into mass, and we use E equals delta mc squared for that. Delta m being what we call the mass defect, what the difference in total mass is between before and after. Of course, E equals mc squared involves joules and kilograms, but here's the shortcut. 1 U of mass converted into energy gives you 931.5 mega electron volts. This will be in your formula sheet. It's a much nicer conversion factor to work with. This energy needed to separate out the nucleons is called the binding energy. Now, if we draw a graph of average binding energy per nucleon against mass number, we end up with this shaped graph. Now, to all intents and purposes, average binding energy and total binding energy follow basically the same pattern, so they're essentially the same thing. So maybe that'll help you understand what's going on here. Remember that binding energy is the energy needed to separate a nucleus out into its constituents, which means the one at the top requires the most energy to separate out the nucleus. This is the most stable isotope, therefore, and it happens to be iron 56. The little spike on the left is helium-4, by the way. It's an uncharacteristically stable isotope compared to its immediate neighbours. That's why it's emitted during alpha decay. However, when nuclear events occur, such as fission, fusion, decay, they don't involve nuclei completely split into their constituents, of course, or vice versa, but just rather turning into other nuclei, which are more stable, meaning they always move up the curve as their total binding energy, and therefore their average binding energy per nucleon as well, has increased. We can think of them as falling down a potential well, meaning they would need more energy to get out. Fission is the splitting of a nucleus, whereas fusion is the joining together of them. In both cases, energy can be released so long as the binding energy has increased. They fall down this imaginary potential well, and therefore climb this curve. That means the isotopes to the left of iron 56 release energy if they undergo fusion. To the right of it, the same is true if they undergo fission instead. If you were asked to calculate the binding energy in an interaction, all you have to do is find out the mass defect and then just times by 931.5 to give you the binding energy in mega electron volts. Activity is given by the simple equation A equals lambda n, where n is the number of undecayed nuclei, not neutrons in this context, and lambda is the decay constant in seconds to the -1, but it could also be another unit for time to the -1 instead. The decay constant is the probability that a single nucleus will decay in that amount of time. I've dropped the minus that's sometimes in the equation, as it's only important when deriving the exponential decay equation, which you don't need to do for your exam. We're not going to do it now, but the equation that we end up with is A over A0, that's just activity now at time t, compared to initial activity, is equal to e to the power of minus lambda t, where t is the time and the unit of that must be equivalent to the decay constant in order for this to work. You might see the equations written differently in the formula sheet, but I think it's useful this way for us to see it's merely a ratio of activity now compared to initial activity. So it's just a number between 0 and 1. It also works for n over n0, that's number of undecayed nuclei left, and it also works for mass too. If you need to rearrange for lambda or t, we do the natural log on the other side. You might say ln if you're weird. So natural log of A over A0 equals minus lambda t. The minus is important here. If activity is halved, the time t is the half-life by definition. So that's where t half equals natural log 2 over lambda comes from. So if you're given a graph of activity, you will invariably have to find the half-life from it and then calculate lambda as natural log 2 over this half-life. Then reuse lambda in the full equation. As gamma radiation is emitted in all directions, it falls away inverse squarely with distance, so intensity is inversely proportional to distance squared. So we can say that I1d1 squared equals I2d2 squared. Intensity can also be replaced with count or count rate, the amount of radiation detected over a certain time, say a minute. Don't forget your background count, of course. If you draw a graph of count against 1 over d squared, you'll likely get a straight line that doesn't go through the origin. This is because the distance measured won't usually take into account that the radiation isn't being absorbed right at the end of the tube, so there might be a systematic error of a couple of centimeters or so. If the graph curves when you get close to the source, that implies that there's probably some alpha or beta being emitted as well. It's believed that stars are the result of dust and gas particles in clouds. We call such a cloud a nebula, and these particles are attracted to each other due to gravity. The cloud becomes hotter and more dense until fusion starts to occur. The star will remain stable so long as the outward pressure from fusion and the force of gravity pulling inward remain balanced. We say it's in the main sequence stage of its life. When a star dies, the outward pressure increases, which causes it to expand. This turns it into a red giant if it's a star of a similar size to our sun, or a super red giant if it's much bigger. A red giant will then collapse once all the fuel for fusion has run out, leaving a white dwarf, and then a black dwarf once it's cooled. A super red giant explodes. We say it's gone supernova, leaving a very dense neutron star at the center, or an even more dense body that causes a black hole there. The outer layers of the supernova move away, forming new nebulae from which new stars could be made. Nuclei fuse together to make heavier elements. Some of these could only be made as a result of the huge amount of energy that's released from a supernova. Luminosity of a star is just the term we give to its total power output in watts. It's given by Stefan's law. L in watts, or power in watts, equals the Stefan constant times the area of the star, so 4 pi r squared, times its surface temperature in Kelvin to the power of 4. For the sake of physics, we can treat stars as perfect black bodies. We assume that they emit and absorb all wavelengths of light equally. This allows us to draw this graph of energy emitted against wavelength. We can see that it increases with a shorter wavelength because, well, shorter wavelength means higher frequency, which means that the waves have more energy. But it does reach a peak and then comes back down. According to classical physics, this energy should carry on increasing with shorter wavelength. But this implies that a star has infinite energy to give out, which is impossible, and that's because of some quantum mechanics malarkey. As it happens at around ultraviolet wavelengths, this is called the UV catastrophe. The wavelength that emits with the highest energy we call lambda peak. The hotter the temperature, the shorter this wavelength is, and the higher the peak. This peak wavelength is given by Wien's law. Wavelength times temperature in Kelvin equals Wien's constant, which is 0.0029. We can draw a Hertzsprung-Russell diagram, just a graph of luminosity against temperature, to show what stars exist out there. Just remember that temperature decreases as you go along the x-axis. Main sequence stars follow this line here. Luminosity follows temperature, which is what we would expect. White dwarfs are small but hot, while red giants are huge and relatively cool, so they occupy the spaces above and below the line. Astronomical distances are so large that we usually use the unit parsec instead of meters. It's short for parallax second. This second isn't a time though, but it's a 60th of a degree, which is what we call an arc second. 1 parsec is the distance at which 1 AU subtends 1 arc second, 1 AU being 1 astronomical unit, which is the mean radius of the Earth's orbit around the Sun. We can also use the light year instead. That's the distance light travels in 1 year. We have a good idea of what wavelengths of light are emitted from stars. However, when we look at distant stars and galaxies, these wavelengths appear longer. They're shifted towards the red end of the spectrum. The light has been redshifted. Much like when the pitch of an ambulance siren drops when it's moving away from you, like that shows that the galaxies must also be moving away from us. And this is the case in every direction we look. Not only that though, the light from more distant galaxies is even more redshifted, suggesting they're moving faster away from us, receding faster, we say, at a faster rate. This implies that if we go back in time, all of these galaxies appear to have originated from the same point in space. This is therefore used as evidence for the Big Bang theory, and that the observable universe is still expanding. The other piece of evidence for it is CMBR, cosmic microwave background radiation. Outer space might look dark, but we can detect microwave radiation being emitted from very far away from all directions. This could be a result of matter still cooling down. So it seems we're looking at the edge of the Big Bang. We can give the amount of redshift or Doppler shift a number. This is equal to the recessional speed divided by the speed of light. And it so happens it's pretty much equal to the change in frequency or wavelength divided by the original value. The shift in wavelength can be seen on the emission spectrum for a star. Characteristic wavelengths we observe emitted from gases here on Earth are generally shifted to the longer red end. Sometimes a line will appear to be split in two though. This can be due to a binary star system. Two stars that are trying to orbit around each other, so end up just orbiting around a common point between them. So we have different redshift for both, producing two separate lines. Twice every orbit, the lines recombine into one. The Hubble graph is just a graph of the recessional velocities of all the observable galaxies against their distance. They're proportional, which is why the Big Bang theory is widely accepted. Making an equation, we say that V is equal to h0d, where h0 is the Hubble constant, the gradient of the graph. This has the unit seconds to the -1, therefore the reciprocal of this gives us seconds, the value of which in theory is the age of the universe. However, often the graph won't be in meters per second and meters, it'll be in kilometers per second and megaparsecs. If you're asked to calculate h0 in seconds to the -1, you'll have to convert these first. You always want to make accurate measurements, reducing any errors and uncertainties to a reasonable degree. When measuring any length, the ruler should be as close to the object as possible to avoid parallax error. You want your eye to be in line with the point on the ruler too, for the same reason. Parallax error is a random error. It won't be the same every time. If it's not possible to have them close together, say when measuring the extension of a spring, you can use set squares, just a right-angled triangle, even made out of a piece of card, to accurately show where it lies upon the ruler. It's also a good idea to use one between the ruler and the flat surface it's on, say the table, to ensure that the ruler is indeed vertical. The resolution of a ruler or a meter rule is usually 1 millimeter. That's the smallest difference it can measure. There can be a large random error when using a stopwatch due to reaction time. To mitigate this, you should always do repeats and calculate a mean. This is also true when taking measurements, say with a vernier caliper or micrometer, for example, when you're finding the thickness of the wire in the Young modulus or resistivity experiments. Digital instruments will give you a value on the screen. All you have to do is take the reading, like a digital voltmeter. However, sometimes it's more useful to use an analog instrument. In this case, your eye must be in line with the needle to avoid parallax error. Sometimes they have a mirror behind to help you with this. You might have to choose one that has an appropriate full-scale deflection for your measurements. That is, the maximum measurement it can make. This is usually 1, 2, 5, 10, 50, 100, etc. Let's say we find out the maximum voltage we're going to have to read in an experiment is 6 volts. The appropriate full-scale deflection would be 10 volts in this case. 1 volt would be too small, and 100 volts would result in inaccurate readings because the resolution would be too large and the uncertainty would be massive. A micrometer has a much higher, or I prefer saying smaller, resolution, usually 0.01 millimeter, that's 1/100th of a mil. Firstly, it's a good idea to calibrate it. Close the jaws with nothing between using the ratchet on the end. This ensures you don't over-tighten them, which would result in the jaws being compressed, giving the wrong measurement. If it says 0.00 millimeters at this point, it's all good. If not, there is a zero error, a systematic error. Systematic means it will be the same error every time. To mitigate this, just subtract the error from every measurement. A vernier caliper also has 2 scales. The 0 on the slide tells you how many millimeters, then the vernier scale gives you the tenths or sometimes 20ths, that's 0.05 millimeters, you have on top of that. A vernier scale works because its lines are spaced such that they don't line up with the main scale. However, one of these lines will line up with the main scale. That's what you take as your tenth of a millimeter. So this would be 8.7 millimeters. It can also be used to measure the depth of a hollow object, say a tube, using the rod that comes out of the other end that goes into the tube and the edge of the caliper rests on the top. Then you just read it as normal. Uncertainty is the idea that even if you avoid parallax error, zero error, etc., no measurement will ever be completely accurate because there's always a bit of rounding involved in every one you make. For example, using a thermometer with a 1 degree Celsius resolution will require you to decide if the liquid is closer to, say, 27 or 28 degrees. In chemistry, say, you'll likely say that this temperature therefore is 27 plus or minus 0.5 degrees. Now, you will likely get the mark if you say that in a physics exam as well, but many argue, including myself, that there's every possibility that you might think the liquid is closer to 27 when it's actually closer to 28. That means the true value is not within your uncertainty. That's why most questions expect you to state the uncertainty as being equal to the resolution itself. So this would be 27 plus or minus 1 degree C. The uncertainty of a digital instrument can be inferred to be just one of the last digit, or it can just be half of that, which is a little bit more appropriate than if we're actually doing a measurement with a ruler or thermometer. That involves a judgment call. Finding the uncertainty in a mean value, all we do is find the range of the values, then half it. That's the maximum, take away the minimum, by the way, not the first, take away the last. Drawing a line of best fit on a graph allows you to find a gradient. However, sometimes the points will have error bars to reflect the uncertainty. If that's the case, you can also draw a line of worst fit too. This is a line that has the maximum or minimum possible gradient while still crossing through every single bar. Note that means it might not hit the ends of the first and last error bar, but that's okay. We then find the difference between the gradient of the line of worst fit and the line of best fit to find the uncertainty. Alternatively, you could just draw the 2 lines of worst fit and find the mean of the 2 to get the gradient, and the uncertainty will be half their range like any other mean. If you add or subtract 2 values that have an uncertainty, then the total uncertainty is the sum of the 2 uncertainties. If you're using a ruler that you can move so the 0 can be lined up with the edge of whatever you're measuring, the uncertainty will be equal to the resolution. However, if the ruler can't move and you have to find the measurement by finding the difference between 2 points, then the uncertainty will be double the resolution. This is because we've essentially just combined 2 uncertainties, or rather 2 absolute uncertainties. Absolute uncertainty is your normal uncertainty. It has a unit, just like the measurement. But what if you're multiplying or dividing values that have uncertainties instead? In this case, you convert the absolute uncertainties into percentage uncertainties, and then you add them all up regardless of whether it's being multiplied or divided. So let's say we have these measurements, which we put into an equation to calculate an answer. Here are the uncertainties in percentage form as well, and I've added them up to give the total percentage uncertainty. Uncertainties always increase, by the way, regardless of whether you're adding, subtracting, multiplying, or dividing. Once you have the total percentage uncertainty, you need to turn this back into an absolute uncertainty for the final calculated value. Just multiply it by the percentage uncertainty as a decimal, and boom, you're done. We usually try to obtain a straight line graph in physics experiments, which allows us to find a gradient and therefore the relationship between the two variables on the axes. Variables aren't always directly proportional though, of course, but if we know the relationship, we can plot the right things on the axis so we do get a straight line. For example, with the stationary wave on a string experiment, we know that the frequency is proportional to the square root of the tension, or f squared is proportional to t. So if we plot f squared on the y-axis, t on the x-axis, we'll get a straight line. If we have some sort of inverse proportional relationship, then 1 over something must go on one of the axes. Log graphs are powerful because they allow us to find the relationship between two variables if we don't know it. Prime example of this is what Kepler did to coin his third law. He saw that the further away planets were from the Sun, the longer their time period. But he needed to find out exactly how they were related, as t clearly wasn't proportional to r, but r to the power of something instead. If we take the planets in our solar system and plot log t against log r, we get a straight line. It doesn't matter what log base we use, by the way, it works even for natural log ln. A graph with log values always gives a straight line. The gradient is the important thing here. Usually this is what gives us the relationship. In this case, the gradient is 1.5 or 3 halves. The general straight line formula is y equals mx plus c, or in this case log t equals 3 halves log r, plus some constant which is our y-intercept. Let's call it log k. From there we have two log identities we need to use. First we can take the 3 halves and make it the power on the r. Then we can also say that the sum of two logs is equal to the log of the two things multiplied. So on the right we have log kr to the power of 3 halves. Delogging both sides, we see that t is proportional to r to the power of 3 over 2, or t squared is proportional to r cubed. Even if logs aren't involved, you still need to be able to interpret a graph in terms of y equals mx plus c to produce an equation. Bear in mind that sometimes it's only one of the axes that will be a log, and just remember if you delog one side, in this case it's 10 to the power of the other side, or it would be e to the power of the other side if it's a natural log. Finally, it's possible you'll be given a graph that has an actual logarithmic scale. It's non-linear. In this case, the first line is one of that order, and the lines then get smaller approaching 9, and then it goes to the next power up, so 10, 20, 30, up to 90, then 100, 200, etc. Reading off these graphs often requires you to make a judgment call with values between the lines, so just remember that going halfway to the next line isn't actually half the difference. It's not 5, but it's more like 3. So I hope you found that helpful. Leave a like and a comment if you did. Click on the card to go to the playlist for all the papers, and I'll see you next time.